Yesterday we stopped in the fourth case, right? We did not proceed with the fourth case, which is the continuous case with two variables now. So there is a theorem for that, isn't there? So we did not get into the theorem. We just got into this notation as to how do we write the Jacobian. That's it. Uh, but before we get into this, I wanted to tell you something. Like in the previous case, we looked at this, right? Uh, in the single variable case, uh, the PDF of this one is nothing but this one and this one. We've seen this. So the problem here is instead of dx by dy, if you write dy by dx, then that is a problem. Because if you want to use dy by dx, then you have to write it in the denominator. So, like, how do you? There is one intuitive way of remembering this. How do you know if it is dx by dy or dy by dx? We know that if you integrate any PDF, uh, you're supposed to get the same thing. Like if you integrate from minus infinity to infinity, you're supposed to get 1. You're supposed to get 1. This we know. So if you want to find the PDF of y, you just have to send dy to the other side. So that is how you can intuitively keep in mind that if PDF of y is nothing but PDF of x dx by dy. It's like you're sending dy to the other side. And there is a mod because PDFs have to be like non-negative. That's why there's a mod. So intuitively you can keep intuitively you can keep no, I mean intuitively you can uh, remember the formula, something like that. That's it. Or else there is nothing much in this. If you already remember it, that is fine. Okay. Anyways, now we'll get back to our theorem. What is the theorem? Previously, where is previously? Previously, our g of x is there, right? G is differentiable and g is monotonic. Are there any such conditions over here? We'll see. Because when we have two variables, how do you say if a function is increasing or decreasing? We wouldn't know, right? Because if there's a function in two variables, you can plot it in 3D. Let's say the function looks something like this. Uh, Maybe something like this. This is some 3D function. Now, how do you know? See, if you can plot a single variable function in 2D, we can say, oh, it is increasing, it is decreasing. But that's not the case in 2D, right? Now, which direction is increasing, which direction is decreasing, we wouldn't know. So that is one problem, but I don't think we will face those problems because the questions will ensure that something is happening. So, okay, fine. We'll just get into the examples now. So, like, there is more to this problem, but in the exam point of view, we wouldn't face those problems. We don't even know what those problems are, but it is something about the uh, increasing and decreasing nature. How do you know, or when do we decide that a two variable function is increasing or decreasing? We wouldn't know. Okay, fine. So let x1, okay, x1 and x2 has some joint probability density function. Okay, fine. Density because it's continuous. Mm, So y1 and y2 are some functions of x1 and x2. So g1, g2. So they're saying assume that the functions g1 and g2 satisfy the following conditions. What are the conditions? The equations y1 equal to this function and y2 is equal to g2 can be uniquely solved for x1 and x2. So we're taking this assumption. So previously in the single variable case, we assumed g is differentiable and g is monotonic. So instead of that condition, we are assuming this condition. So this is dealing with the problem that I just told about before, the increasing decreasing problem. So instead of increasing decreasing, now we are assuming the solutions of y1 equal to g1 and y2 equal to g2 are unique. So and the unique solution is x1 equal to h1 and x2 equals to h2. So it's like similar to 1 1, like you have one input, you have one output. So for one output you have one input, something like that. So this is one assumption, and the other assumption is the functions g1 and g2 have continuous partial derivatives. Okay, so we have two assumptions. One is that you have some unique solution in the sense, if you solve y1 if you solve the y1 equation, y1 equal to g1 equation and y2 equal to g2 equation, you will get x1 and x2, where x1 is a function of y1 and y2, and x2 is also a function of y1 and y2. So some unique solution you got. That is one assumption. The other condition is that the partial derivatives must be continuous. You know continuity, right? If the limit value is equal to the function value, then the function is continuous. So here the partial derivatives must be continuous. Okay, nice. Okay, two assumptions. It shouldn't be a problem. The questions will be given in such a way that all of these conditions are achieved. So uh, we don't have to check if these conditions are being satisfied or not. We can just go about our way solving through the thing. We don't have to verify or some check if these conditions are being satisfied. But this is the Jacobian. So Jacobian will be there. So where is the main theorem? Theorem. This is the theorem. Nice. So it's the same thing. Same thing in the sense, now instead of one variable you have two variables. So let me write that once again. So one variable we know, two variables it's okay. First let me write it in one variable. One variable looks like this, right? uh, dx by dy, or else dy by dx. If you okay, that was one variable. If you look at the notation of Jacobian, when I write Jacobian y1 comma y2, it means y1 and y2 come in the dou y the dou y1 dou y2 will come in the denominator. Not exactly, it's not a fraction, so it will come at the bottom, dou y1 and dou y2. Similarly, if I write Jacobian x1 x2, it means x1 and x2 are appearing at the bottom, dou x1 dou x2 are appearing at the bottom. So keeping this in mind, so I will just write what is the PDF of y1 and y2. You can just look at the one dimensional case and write this one. So how do I write this? So okay, fine. This is a double variable, right? So you'll have y1 y2 y1 y2. So x1 comma x2. See, I'm just writing whatever. I'm taking inspiration from the one dimensional case. I'm drawing parallels between them. Okay, x1 x2. Now we will get a mod. What do we write inside the mod? Do we write Jacobian of x1 x2, or do we write Jacobian of y1 y2? If you notice here in the one dimensional case, dy is in the denominator. No, denominator in the sense we are differentiating with respect to y. So in these two Jacobians, which is the Jacobian that is differentiating like with respect to y? It is this one, because we've just seen Jacobian y1 y2 means we're differentiating with respect to y1 and y2. So here you will get Jacobian y1 y2. Let's see, am I right? Let me just verify. Yes, fine, I'm right. This is fine. So this is the two-dimensional case. I just took inspiration from the one-dimensional case. And similarly, if you want to use Jacobian of Jacobian x1 x2, then that will go in the denominator. So x1 x2 Jacobian x1 x2 modulus. So what do you mean Jacobian x1, x2? It means you're differentiating with respect to x1 and x2, which is the case here, right? In the one-dimensional case, in the denominator, we are differentiating with respect to x. So same story over here. So the thing is, in one-dimensional case, you simply have dy by dx or dx by dy, that is there. But in the two-dimensional case, you get a Jacobian. That's it. Jacobian is a determinant. Jacobian is a determinant. Fine. Now we know that what do we know? We know y1 is a function of x1 and x2, and we know y2 is also a function of x1 and x2. And we assume that if we solve this, we get a unique solution such that x1 is a function of y1 and y2, and x2 is also another function of y1 and y2. So I can simply substitute this in the theorem. What do I get? I will get f of y1, f y1 y2 small y1 small y2. This is nothing but, now I'm replacing the x, the small x I'm replacing. So what will I get? X1 is nothing but h1 y1 y2, and x2 is nothing but h2 y1 y2, and Jacobian. So Jacobian. Okay, so my RHS is in terms of y1 y2. Yes, fine. So Jacobian, I can just leave it that way. What else? It's fine. You can replace y1 with g1. That is also fine. Whatever it is, it depends on whatever we are doing. So it's fine. I can leave it like this, or else I can write the same thing this way. Or else, if you're taking Jacobian with respect to x1 x2, I can write it here, and x1 x2. Fine. It's the theorem now. See, now I just rewrote the theorem. You don't have to memorize anything. If you know the one-dimensional case, you can write the two-dimensional case as well. Okay. And see, we know x1 is a function of y1 and y2, and x2 is also a function of y1 and y2. Proof, we don't have to look at the proof. It is fine. So, okay, fine. We found some PDF, right? What kind of a PDF is this? This is a joint random variable PDF. Like you have two variables. It's not one variable. So it's a joint PDF. Joint density function. Yes. So joint density function. Fine. Jacobian. Fine. So x1 and x2 are nothing but h1 and h2, right? So you can replace x1 with h1. That is fine. And there is this property, like how dy by dx is equal to 1 by dx by dy. Similarly, Jacobian here, same property. Okay, so here they gave y1 is equal to x1 by x2. So y1 here is a function of x1 and x2. Y2 is another function, but only x2 is there, but you can still write it as a function of x1 and x2. There's no harm in that. It's just that in y2, the x1 just never appears. Okay, maybe we will do this small example and then we can just look at the other examples. Okay, fine. Instead of me solving, it's already here, so we'll just see. So if you rearrange, like if you solve for x1 and x2, you will get something. So you will get x1 in terms of y1 and y2. You will get x2 also in terms of y1 and y2. So here the h1 of y1 y2 is y1 into y2, and the h2 of y1 comma y2 is just y2. I'm talking in terms of this one, this one. So y1 and y2 are functions of x1 comma x2, and x1 and x2 are functions of y1 y2. So that is what I'm talking about. G1 G2 H1 H2. Here G1 is x1 by x2, and G2 is simply x2. Here H1 is y1 into y2, and H2 is simply y2. So what is this person trying to do? Okay, this person wants to compute this one, Jacobian y1 comma y2. What does it mean? It means you're differentiating with respect to y1 and y2. What are you differentiating? X1 and x2. So in the first column, you'll simply okay, let me write. So I got x1 as y1 y2, and x2 as simply y2 y2 y2. Fine. So this person wants to find the Jacobian with respect to Jacobian y1 y2. So we are differentiating with respect to y1 y2. So first you will differentiate with respect to y1, and then you will differentiate partial. You're taking partial derivatives with respect to y2. What will you get here? Yes. So we know x1 is y1 y2. Partial derivative with respect to y1, what will you get? Just y2. And x2 is y2. Partial derivative of y2 with respect to y1 is just 0 because nothing is there. Uh, you people know how to do partial derivatives. I think that is nothing much to be told here. This is 1. So it's a determinant, right? So you find the determinant. You will get y2 minus 0, so y2. So Jacobian is y2. Jacobian is y2. The same thing. Jacobian is y2. You can do the other Jacobian as well. So if you want to find, you don't have to do both of them. You can just do any one of them. So okay, we'll write. What do we have? We have y1 is equal to x2 by x1, and then we have y2 is equal to x2, right? Where is this? X1. Okay, x1 by x2. I will do this Jacobian as well, and after doing this Jacobian, you'll probably understand which Jacobian should I find so that my calculation becomes simpler. So we will find the Jacobian x1, x2 as well. So what is this? This is just dou y1. You differentiate first with in the first column you differentiate with respect to x1, and in the second column you differentiate with respect to x2. Now y1 is x1 by x2. So differentiation with respect to x1 would be just 1 by x2, and this is just 0. There is no x1 component. Y1. So I'm differentiating with respect to x2. So what will I get? I'll get minus x1 by x2 square. And here, what will I get? I'll get 1. Here the Jacobian is 1 by x2. Yes. So 1 by x2 is nothing but 1 by y2 because x1 is equal to x2. If you want, you can verify. Here, Jacobian of y1, y2 was y2. Jacobian of x1, x2 was 1 by x2. And we can verify that Jacobian y1, y2 is equal to 1 by Jacobian x1, x2. It is simple because y1 is equal to y2. We know that. So whatever you do, it's fine. But if you notice here, the derivatives kind of get complicated. Not so complicated, but maybe because here you had to use the u by v rule. But in the previous case, everything was very much simple. So looking at this, maybe you can decide, like look at these equations and decide, finding the partial derivatives of which kind of equations makes my job easier. Is it for this set of equations or this set of equations? Usually, if you have simple looking equations, probably you'll just go ahead with that. Here you have something like numerator by denominator. So your partial derivative might look complicated. Complicated in the sense, not simple. You'll get something like this. You'll have to deal with it. So you have the choice now. You can, uh, depending on your choice, you just find the Jacobian. The person whoever made the PPT took the right choice. They did not find Jacobian x1, x2. They found Jacobian y1, y2 because it is easy to solve for it because it looks simple, right? Y1 into y2, y2. It's simple to solve. So it is simple to find the Jacobian as well. So okay, so what would that mean? Okay, fine. Instead of me solving, just see. Okay, so there are two planes. One on the left hand side, we have the plane of x1 and x2. On the right hand side, we have the plane of y1 and y2. You will have to know how to make these kinds of planes because when you're integrating, maybe in some questions that come after, when you're trying to integrate something, you'll have to know in which region are we integrating. Then the limits of integration will change and all that will happen. Maybe in the tutorial we have some similar questions, so you could go through that. Okay, anyways, so after finding Jacobian, what do we do? Okay, before doing any of that, they tried to plot something. They've tried to plot x1, x2. Look at the constraints: 0 less than x1 less than x2 less than 1. Let us just plot this. How do we start plotting? They gave 0 less than x1 less than x2 less than 1. They gave this, so now how do we plot this? So first step is just make the axis. This is the x1 axis. This is the x2 axis. Now, what you do is just take the inequality and consider it to be an equality. So, what do I mean? So, just draw where is x1 equal to 0. Draw where is draw which this one x1 equal to x2, and draw x2 equal to x1, and just see. Just draw these three lines, and then we'll see what to do about it. So, x1 equal to 0 is this line. So, this is x1 equal to 0. The other one is x1 equal to x2, which is this line. This is x1 equal to x2. The other one is x2 equal to 1. So where is x2 equal to 1? x2 equal to 1 is here. So this is x2 equal to 1. x2 equal to 1. So we got our lines. Now we have to see which region are we talking about. So when I say x1 is, uh, when I say 0 is less than x1, it means x1 is more than 0. What is x1? So x1 more than 0 means this region. Here x1 is more than 0, this region. Fine. And x1 less than x2. Where is x1 less than s2? X2. So just take a point. If I say, see, x1, you have two regions, right? You have this region, you have this region. You have to decide which region is x1 less than x2. When in doubt, just take a point. This is 1 comma 0, right? Just substitute 1 comma 0 in this inequality. What do you get? 1 less than 0. Is that true? 1 is not less than 0. That means whichever region 1 comma 0 belongs to, that will not be the region. So this is not the region. The opposite region is correct. So what is the opposite region? This one. This is the other region. So this will represent x1 less than x2. If you want, you can verify. Take any point in this. You can take minus 1 comma 0. Is minus 1 less than 0? Yes, it is. So this is the correct region. The opposite, the other side. And now we have to check where is x2 less than 1. x2 less than 1. First of all, where is x2 equal to 1? x2 equal to 1 is here. So x2 less than 1 means you can see, you can take the points and verify. It will be the region below this line. So our region will be the intersection of all these regions, which is here. If you notice, this triangle is the intersection of all our constraints. So this is nothing but 0 comma 0, this is 1 comma 1, and this is 0 comma 1. So that is what they plotted here in the graph. Left side, left side is our thing. So Sx is the range of x. So x belongs to this set, this triangle. So every point is there, right? So you'll get your x1 comma x2 from this triangle. Now the thing is, now we have to convert this to the plane. Which plane? The other plane, which is y1 y2, y1 y2. Now how do I draw y1 y2? Is first make a note of the relations. Y1 is x1 by x2, and y2 is x2. Fine. Now that we know what is y1 and y2 in terms of x1 and x2, the first thing that you're supposed to do is these three lines we have, right? Just try to find the representation of these three lines in the y1 y2 plane. In x1 x2 we did this. Even in y1 y2 we will first draw the boundaries. These three are the boundaries, right? So we'll see one by one. So first one is we'll look at the first line. So okay, I'll make a number. So x1 equal to 0. Where is x1 equal to 0? This is the first line. X1 equal to x2 is the second line. X2 equal to 1 is the third line. Fine. So first line is x1 equal to 0. So I'll substitute x1 equal to 0 and see what I'm getting. So when I say x1 equal to 0, what do I get? I get y1 is 0 and y2 is not affected. So y2 can be anything. Y2 is anything. Or I can simply write y2 belongs to real numbers. If x1 is 0, now what does this mean? It means I have to plot y1 equal to 0. Where is y1 equal to 0? Y1 equal to 0 is here. This is y1 equal to 0. So how did I get y1 equal to 0? I got it from line number 1. So it means my first line got transformed as this one. So I'll call this line number 1. Or else I can mark it. So in the PPT, they just marked it this way. So this is line number 1. Okay, now we'll go to line number 2, x1 equal to x2. x1 equal to x2. Now I will just substitute it in the relation, the y relation. What will I get? So y1 will be 1 because x1 y1 is x1 by x2, and y2 will be x2. X2 is just x2. We don't know what it is, isn't it? We don't know. X2 is just x2. So what does that mean? Because uh, x2 can be any number. X2 is any real number. So that means y2 also belongs to real number. But you have to be careful. Can x2 be 0? If x2 is 0, y1 also has to be 0 because x1 equal to x2. But then 0 by 0 is undefined. So we will say that x2 belongs to real numbers except 0. But first, what does it mean? First, we'll draw the line y1 equal to 1. Where is y1 equal to 1? Y1 equal to 1 is here. This is this 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 is y1 equal to 1. And I told y2 is equal to x2. So it means y2 can be anything. Y2 can be anything, but then we are not sure whether y2 can be 0 or not. So I will just pluck this point out. I'll just plug that point out because if x2 if y2 is 0, it means x2 has to be 0. If x2 is 0, it means x1 is also 0. That would mean y1 is 0 by 0. So we'll just remove the case where x2 is 0, which would mean y2 can't be 0. So I'll just pluck this point out. Anyways, so this was our second line. So I'm just using two lines. What is the third one? X2 equal to 1. So if I substitute x2 equal to 1 in the equations of y, what will I get? Y1 is just x1 and y2 is 1. So x1 is any number. X1 is some real number, isn't it? More specifically, the x1 and x2 must satisfy this constraint, right? More specifically, but I'm just drawing the general line, so I'm just considering that they're coming from real numbers. But we'll see. We're just drawing the boundaries, right? We'll come to the constraints later. Okay, fine. So where was I? Y2 equals to 1. So y2 equals to 1 is basically this line. This is y2 equal to 1. This is our third line. So y2 equal to 1, it means y1 is going from, okay, y1 is what? Does y1 belong to real numbers? Will there be any problem if y1 is 0 or something? It shouldn't matter. Finally, we got our three lines, right? We got our three lines. So what does it mean? So the first line in the x plane, the x1 x2 plane, got transformed and it came here. The second line, which is this x1 equal to x2, that got transformed into this straight line. And the third line, which is this one, I think it remained there itself. So we have this one. Now the thing is, now we have to find where is our region. Where is our region? It is usually enclosed by the boundary lines, but here we have only three lines. We don't have an enclosure. But let's just see. We know that where is this? The constraints are 0, less than x1, less than x2, less than 1. So can we try to find, because see, intuitively you can see that boundary, the region bounded by these lines should be somewhere over here. You can see that intuitively. If you can't see that intuitively, you can use math to find that this is supposed to be here. Okay, I'll show you math. So when I say x1 and x2 are greater than 0, it means x1 and x2 should lie in the first quadrant. And if x1 and x2 are in the first quadrant, what does it mean? It would mean y1 is like positive, right? Or non-negative for that matter. Oh, okay, x1 and x2 can't be 0. So, okay, that is fine. So, if x1 and x2 are strictly positive, it means y1 is strictly positive and y2 is also strictly positive. What do I mean by y1 and y2 are strictly positive? It means you have to look at the first quadrant. Okay, now we directly got a region. Now our region is basically this one, right? The inside portion. You can see there are more steps that you can do to mathematically show that this is a region, but intuitively also you can say this is a region. Okay, anyways, okay, let me just show. Uh, Fine, first quadrant. Now, how do I say this is my region? So, if x2 is less than 1, what does that mean? If x2 is less than 1, it means y2 is less than 1. If x2 is less than 1, because see here, y2 is equal to x2. If x2 is less than 1, then y2 also must be less than 1. So, where is y2 less than 1? Y2 less than 1 is here, this region. This is y2 less than 1. Now, we got a region which is basically this one. Now we can boil it down more. How do I boil it down more? x1 is less than x1 is less than 1. So if x1 is less than 1, what does it mean? Uh, if x1 is less than 1, it means y1 x2 is less than 1 and x2 is nothing but y1. So am I does this even go anywhere? Y1 y2 is less than 1. No, I don't think it's going anywhere. Is there any simple way to go about this? How do I show that y1 is less than 1? Okay, fine. So we know x1 is less than x2. So x1 by x2 will be less than 1. And I know x1 by x2 is y1. So y1 is less than 1. So y1 is less than 1 means now we have to look at this region. So the intersection will now be this one. So intuitively also you could have told by looking at this that this is the region, but mathematically I've shown you how to like find the region. So okay, anyways, so what did we do? We just transformed this region in x1 x2 plane into the y1 y2 plane. So the points are 0 comma 0, 1 comma 0. Mind you, here the region does not include the boundary. So because x1 and x2 are strictly positive, right, from the constraints. So x1 and x2 can't be 0. So it's only the inner part. The boundaries are not included. And this is 1 comma 1. This is 0. So a triangle in the x1 x2 plane became a square in the y1 y2 plane. So this is a transformation. Now it's simpler. If there's any integration to do, you can just integrate along this across this surface. Fine. So that is how they got their region of y. Okay, nice. Now they're applying the theorem. So PDF y1 y2 is nothing but PDF x1 x2, which is given to be 2, right, in this example. PDF is 2, so simply 2. It's a constant. Fine. So you get a constant 2, and then you multiply it with Jacobian, with Jacobian x1 x2 or y1 y2. Y1 y2. So Jacobian y1 y2 is mod y2. You have to take the mod of the Jacobian. So 2 times mod y2. And the region, yes. So you have to write the region as well. So careful. How do I write the limits of the region? Okay. Here is the thing. So why do I have to convert? Uh, like why should I draw the region? Because if they ask you to find the marginal probability density, then you have to integrate. And if you're integrating, then you have to write the limits, right? How do you write the limits? By looking at the region. So this is why you have to know how to draw a region, so that you can look at it and then decide. Okay, this is the limit for integration. So y1 lies in between 0 and 1, and y2 lies between 0 and 1. We've seen it's a square, right? 0 to 1, 0 to 1. Okay. Oh, what is marginal? We know marginal, right? It's like if you want to find the marginal probability density of y1, you have to integrate the joint probability density with respect to y2 across its range. So marginal probability density of y1 is nothing but you integrate the joint probability density, which is nothing but 2 mod y2 with respect to y2 across its range. So its range is y2 ranges from 0 to 1. So 0 to 1. Done. So whatever you're going to get from here, okay, they got 1. So the marginal probability density of y1 is basically 1. And where does y1 lie from? Y1 is whatever is there. So 0 to 1. 0 to 1 is the, uh, I think it's right to say domain, but okay, fine. Domain, whatever. So y1 ranges from 0 to 1. Same story. What is marginal probability density of y2? It is nothing but you just integrate the joint probability density with respect to the other variable. So y1 across its range, so 0 to 1. So if you integrate it, you get something. Here you got a function. Okay, fine. You got 2y2. So where does y2 lie? Y2 lies in the interval 0 to 1. What if y2 or y1 lies outside this? 0. You have to write 0. So 0 otherwise. The probability density is 0 otherwise. That is a much um, uh, rigorous way of writing it. Okay, now that we have marginal probability density, we know that the random variables are independent if the joint probability density can be expressed as the product of the marginal probability densities, right? Now, if I multiply these two marginal probability densities, what will I get? 1 into 2y2 is nothing but 2y2. Uh, 2y2, but what is the joint probability? The joint probability is 2, right? The joint probability was 2. Where is it? Okay, wait. Where is the joint probability? Okay, see, a joint probability is 2 mod y2. I can remove the mod because y2 is strictly positive. So joint probability is 2 y2. And The product of the marginals is also 2y2. It means here y1 and y2 are independent. Y1 and y2 are independent. In the probability sense at least. So they're like, uh, how can you say y1 and y2 are independent? Because I can say that y1 is equal to x1 by y2. It's still dependent. How is it independent? That is all fine, but then in the sense of probability, these two random variables are independent. I do not know how to give an intuitive explanation, but in the probability sense, y1 and y2 random variables are independent because the joint probability density can be expressed as the product of the marginal densities. Okay, other examples you can see. I mean, it's just the same. Uh, because in one form of questions, what they will do is, I mean, in the tutorial also, what they did is, uh, they will give you y1, but they will not give you y2. They will give you y1, but they will not give you y2. So in those cases, you are supposed to assume your own y2 and then proceed. The question will be like, they will give you a joint PDF. They will give you a transformation, let's say x1 by x2. They won't give you y2. They won't give you y2 is equal to x2. So the question there will be, find the uh, probability density of y1. So how do you do that? In those cases, if you look at the tutorial also, I think maybe in some of these examples only, maybe we'll see. Then what you're supposed to do is you define your own y2. From there, you do your procedure. At the end, you will get joint probability density, right? From there, you find the marginal of y1. That would give you the answer. So maybe if you look at an example, you will get what I'm talking about. Uh, it's the same procedure. It's just that you have to create your own uh, transformation y2. I think I've seen it somewhere. But there's one question in the tutorial, very similar to, not similar, it's the exact same thing. You have to create your own uh, y2. Okay, it says, see it. This is the question. They gave you a joint distribution, which is small f xy, that is fine. Then they simply gave you a z. They simply gave you a z. Z is nothing but x plus y. Now they're asking you to find the probability density of this z. They did not give you two transformations, they simply gave you one transformation. So to solve problems like these, you have to assume another transformation as well. Why do we have to do that? Because if we have two transformations, we know the procedure how to solve for it. So here they assumed w to be another random variable, and they defined that w is equal to x. Now that we have two transformations, like y1 and y2, here y1 is okay, not y1 y2, just change the names now. So x1 x2 became x and y1 y2 became z and w. So we're just changing the names, but the idea is the same. You have two transformations. Now you can apply the theorem, find the Jacobian and all those things. Okay, now instead of directly doing it, they are rearranging the terms, and they're expressing x and y in terms of w and z. Anything is fine. Just whichever one is convenient, whichever Jacobian is easier to find, just find. Finally, they're applying the theorem on the Jacobian is 1, so or minus 1, so mod Jacobian will be 1, so that is not the problem. So here what happened, they we were successfully able to find the joint probability density of z and w. But the thing is, w is something that we created. It was never given in the question, and the question is asking what is the probability density of z. So in other words, in our case, what are we supposed to do? Simply find the marginal of z. So that way w is going to disappear, and we will get the answer that we require. So the limits you will get if you understand like what is our region, what is the mapping, and all those things. In this case, they simply gave, they did not mention anything about x and y. So you're supposed to assume x and y ranges from minus infinity to infinity. If that is the case, then w also ranges from minus infinity to infinity because w is equal to x and x is ranging from minus infinity to infinity. Okay, fine. So that is why the limits of integration here are minus infinity and infinity. Integrate with respect to w, and then if in the question it is mentioned that x and y are independent, then I can split my joint distribution function as a product of the marginals. So uh, x and y are independent. X is w and y is z minus w, right? So if x and y are given to be independent in the question, I can split my joint probability function as a product of marginals, because isn't that the condition for independence? If the product of marginals is equal to joint probability function, then those two random variables are independent. Even the vice versa is true. If the random variables are independent, then the joint probability function is nothing but the product of the marginals. So in case x and y are independent, I can split the joint density function as a product of two marginals. So that is what happened here, and then you can integrate whatever. Since they did not explicitly mention what is the PDF, we can't integrate because uh, they simply gave f. They did not give what is f. In the questions, we can have what is f. So it could follow some probability distribution, whatever. In the examples, you can see. Uh, at least in the tutorial, there are some nice questions you can see. I don't know if they've given. Okay, here there are two transformations, r and theta. Here also two transformations, u and v. Okay, in the third question, there's only one transformation. So in this case, you're supposed to create your second transformation and just continue with the process that we've seen. And then finally, find the marginal of z. So you can define w as whatever. You can take x1, w is equal to x1, or else w equal to x2. Then you have to find the joint density function of z and w. But since the question is asking about the PDF of z, you have to find the marginal of z. It's the same procedure. And okay, see, in the question they gave x1 and x2 are independent random variables. That means if I write down the joint probability distribution of x1, x2, I can just write it as a PDF of x1 into PDF of x2, the marginals essentially. And look at it, they wrote uniform random variables. It means now you have to use your knowledge. What is the PDF of uniform distribution? So that comes into picture here. So this is how an indirect question is asked. So now you're supposed to know how to write the PDF of uniform. It's a simple uniform. What is the PDF? It is 1 by 1 minus 0. So PDF is essentially 1. PDF of x1 and PDF of x2 is 1. So, okay, fine. Nice. Okay, W is maximum. They're all independent. Okay, they're using the CDF. W is maximum of x1, x2, x3. They're all independent. They have common density. It means their IIDs, independent and identically distributed. PDF is there, CDF is there. Now they're asking us to find the CDF and PDF of W. Okay, CDF of W. What is CDF of W? It means W is capital W is less than or equal to small w. Capital W is nothing but the maximum of capital X1, capital X2, and so on. If the maximum itself is smaller than a value, it means every other value is smaller than W. So that would mean P of capital X1 is less than or equal to W, P of capital X2 is less than or equal to W, and so on. And since they mentioned that x1, x2, x3, and so on are independent variables, I can split this into a product of their product of their individual probabilities. So it will be p of x1 less than or equal to w into probability of x2. The same thing. They just skip this step, but it is understood. You don't skip steps in the exam. You just write everything stepwise. And I can replace x1s with xi's. So see, these are IIDs, so it's very simple to work with. You can split the probability into product product of probabilities. You can replace x1, x2, x3 with xi's, so it's simply x. Fine, you found CDF. PDF is simply differentiation. Just differentiate, done. But when you're writing the CDFs and PDFs, be sure to mention where is the uh, what is the range. So if it's a function of w, where is w coming from? If it's a function of x, where is x coming from? Right, where did I go? No, 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 no. Okay, yeah. So this is minimum. Maximum is. Oh, that was maximum. This is minimum. Is that the case? Oh, that was maximum. This is minimum. So they wrote. What did they write? Okay, I just want to show you. They have to mention. Okay, not here. See, when you write the final answer, you're supposed to write. So if it's a function of y1, where is y1 coming from? And if the answer is different, then for which y1, what is the answer? So you have to mention. You can't just write left side and then leave the right side. You have to write where is y1 coming from. Basically, from the range or the possible values of input. Where is the input coming from? Okay, this is also done. What is there in the next thing? Uh, this one, the bivariate normal bivariate. Where is it? Jointly Gaussian. That is nothing but bivariate and then multinomial. Yes, so multinomial and then bivariate. Interesting things in that slide. Interesting things in that slide. Uh, oh, okay, we wanted to do that first, but then the thing is, we will be using the function of random variable concepts in this slide. So that's why we skipped this and then we went ahead with the 10th PDF. Okay. So there are just two distributions, multinomial and then bivariate normal, or else you can call it jointly Gaussian. Okay, we'll see what is it. So in binomial, we have success and failure, but multinomial is like a very generalized version. You can have so many events. You can have like event A, event B, event C. Unlike in binomial, where where there are only two events, success, failure, success, failure. But then multinomial, that is not the case. You can extend it. You can have n number of events. I will not get into the theory. I will just go to the distribution. You can look at the examples yourself. They're all simple. If you've gone through, because all of us have gone, most of us have gone through permutations, combinations. We know, we've seen all of this. So binomial is fine. You have success and success and failure. Why did I say visit? Oh, revisit was here. Fine. Success and failure. Uh, so if I open the NCK or NCK, right, or NCX, whatever. So it will look like this, right? Binomial. Binomial will look like this. N factorial by x1 factorial, x2 factorial into p1 is the success and P2 is the failure, right? So P1 power x1, P2 power x2. That is fine. And x2 is nothing but x2 is a constant in binomial. X2 is nothing but n minus x. The only thing that's changing here is x1. Only x1 is changing. But in the case of multinomial, you just have to increase the number of variables. So what will happen? You'll have n factorial by x1 factorial, x2 factorial, x3 factorial, x4 factorial, so on. And then p1 power x1, p2 power x2, p3 power x3. So that is what will happen in binomial, multinomial. So we'll see. So multinomial is just an extension of binomial. Uh, where is the formula? So it's just an extension. So instead of x1, x2, now you have, let's say, k number of events. So they're all represented by k random variables, x1, x2, x3, so on until xk. This is the formula, fine, it's just an extension. So what does it represent? So small p1 represents the success of the event of capital X1, and it's like and so on. So small pi represents the probability of the success of the event capital Xi. So so you have k number of events here. So you'll have k probabilities. So small p1, small p2, and small pk, and so on. You have many things. And n is the total number. So if you add x1, x2, x3, so on until xk, you will get the total number of trials. N is the total number of trials. It is called joint probability mass function because binomial is discrete. So multinomial will also be discrete. So you won't have density function, you have mass function. It is joint because you have more than one variable, don't you? So joint probability mass function. Uh, we have to look at some things though. So the events must be mutually exclusive in the sense if one event is happening, it means uh, the other event can't happen, something like that. So if you're tossing a coin, you can't have heads and tails happening at the same time. It's either heads or tails. Or let's say we are guessing uh, we're guessing what day of the week is it today. It can't be Monday and Tuesday at the same time. So they're all mutually exclusive. Today is either Sunday, Monday, Tuesday, Wednesday. Or it's only one day. You can't have 2 days on the same day, right? It can't be Monday and Sunday at the same time. So mutually exclusive. So all the events must be mutually exclusive, and the sum of probabilities must be one. So probability of today being Monday is 1/7, and so is the probability for every other day. So today, uh, is it Sunday today, Monday today, whatever it is, you'll get probability 1/7. Sum of all these probabilities, 7 into 1/7 is 1. It's not like the probability of today being Monday is 2/7, and see, finally whatever you do, if you take the sum, you should get 1. What does it mean? If the sum of all probability is 1, it means all these events are exhaustive. In the sense, there is no other event outside this. So it's like you exhausted all possible conditions. So your events must be mutually exclusive and exhaustive. From where did we get this? We got this from binomial. It's the same story. Even in binomial, they're all mutually exclusive and exhaustive. Anyways, we will not get into theory much. This is the formula. We know how to use it. What are we supposed to take care? The sum of probabilities is 1. That is one property. And sum of all small xi's should be n, because that should give you the number of trials. Uh, so this will become binomial if k is equal to 2. This will become binomial if k is equal to 2. There you have only success failure. Here you can have multiple events, k number of events. Okay, what is marginal? Marginal, not the economics marginal. There, marginal is additional, right? It's like uh, you just want to find the probability density of one random variable. You have k random variables, but you just want to find what is the probability density of just one random variable. What does it mean? It means now you have to uh, okay, fine. We'll just look at an example. It means my other random variables can take any value. right? That is essentially marginal. My other random variables can take any value, but we'll just see. Wait, there's nothing here for marginal. Okay, fine. So what they're telling is, if you want to find the marginal uh, density function of one random variable of a multinomial distribution, it is essentially this. It becomes a binomial. How does it become a binomial? Now, what is going to happen is, now let's say you want to find out the marginal probability density function of xj. Now, what does it mean? Now, you will consider small pj as success and 1 minus small pj as failure. So now it becomes a binomial distribution. So what is 1 minus small pj? 1 minus small pj is the sum of probabilities of all the other variables. So essentially, if you want to find the marginal of a random variable in a multinomial distribution, you just do this. Let's say you want to find the marginal of xj. So xj will follow binomial distribution. The parameters will be n and pj. That's it. It's simple. Maybe if you look at an example, it will make things clear for you. But it's simple. It should be simple to understand, because it's like if any other event happens, it should be considered as a failure. So the sum of all those probabilities will be 1 minus pj. So failure is 1 minus pj, success is pj. Fine. You can give it some thought, but if you want to find the marginal of a random variable in a probability in a multinomial probability distribution, you just have to consider this. That random variable will follow binomial distribution where n is n only, but p now becomes pj, where pj corresponds to the probability of success of event capital Xj. Okay, expected values and variance. Uh, Expectation of x1. See, I just told you that each random variable of a multinomial distribution follows binomial distribution. And we know what is the mean in binomial distribution, right? It's NP. Mean in binomial is NP, and variance is NPQ. And I know that expectation. What is the probability of success of x1? It is p1. So mean is np1. For ex2, it is np2, and so on. Npk. That is fine. What will be the variance? NPQ, right? But for x1, what is the variance? It will be NP1 Q1, and Q1 is 1 minus P1. So that is what they wrote here. For any J, variance of xj is nothing but NPJ 1 minus PJ. That is also fine. Uh, Covariance. Covariance formula is given here. Expectation of uh, covariance xi xj is nothing but xi minus mean of xi into xj minus mean of xj. But then, if you go back to covariance slide, there is this property that it's going to be minus npipj. It's like a property. If you want, you can derive it, but I'm not deriving it. Uh, that is a part of the syllabus, right? Covariance. Okay, that is in unit two. So if you go to unit two, you will probably uh, this will probably seem uh, you will probably get familiarized with it when you look at it. Like, oh, okay, we did this in unit two, but for now we'll just consider this is true. We're not deriving this. If you derive it, you'll get it, but I'm not deriving it. Covariance. So covariance of two random variables which come from multinomial distribution. That is fine, and each of them follows binomial. That is also fine. Uh, Correlation coefficient. Okay, interesting. It's like PIPJ divided by QIQJ. Then you take the under root and take minus. Okay, nice. I mean, correlation is nothing but covariance divided by uh, standard deviation into standard deviation, right? Standard deviation of xi and standard deviation of xj. So from there, I think you can get the values. That is fine. You don't have to memorize this, because see, Uh, this is nothing but covariance of xi xj is nothing but covariance of xi xj standard deviation xi standard deviation xj. We just saw that covariance is n pi pj. Standard deviation is nothing but square root of the variance, right? And variance is nothing but n pq. So pi qi n p j q j. Now you see where this is going, no? So n gets cancelled, and finally you'll get pi pj qi qj under root. So you don't have to memorize. So if you know one thing, the other things will just come about. You don't have to remember this separately. We just saw what is covariance. We know variance is npq. From there we can find correlation. So you don't have to separately remember. Fine. Multinomial is fine. Now you have to go through the examples and see how to use the multinomial. And if they ask you questions like marginal and all of that, I mean, they could directly ask you marginal, or they could give you some word problem, and then you're supposed to realize, okay, here I have to use marginal. I think there was some problem in the tutorial, something similar to this. Uh, some problem about the race, I think. Like, I don't know, elections were happening. How many? I don't remember the question. You can just go like, which candidate is uh, from, I don't know, which race or something like that. Some problem was there, but that is fine. You can go through it. Okay, I think I'm talking about this problem. So the race thing is there. Some kind of election. What is it? Elections? Okay, jury members. Fine. Yeah, I think we had a similar question in the tutorial. I don't remember, but it's fine. You can go through it. So here you have the marginal kind of thing because they're only using one variable. So you'll get the binomial formula. Okay, example. Nice. Okay, nice. Multinomial is done. Now we'll look at bivariate normal distribution. Interesting things are there in this. Interesting things. So we'll see. Interesting in the sense, I mean, I'm telling interesting because, okay, fine, we'll just get into it. Oh, what is bivariate normal distribution? Basically, if you have two normal random variables and if there is some joint probability function for that, that is only bivariate normal distribution. That's it. So if let's say there is some, okay, we'll just go there. Uh, Interesting, no? See, look at the formula there. Look at the PDF, the joint PDF. Okay, so what is happening here? They're like, suppose Z1 and Z2 are independent random variables, each of which has the standard normal distribution. So we have two independent standard normal random variables, Z1 and Z2. And now we are introducing something called X and Y, where X is just some linear transformation of Z1 and Y is also a linear transformation, but then you have Z1 and Z2 in Y. Okay, we know Z1 and Z2 are independent, but now we are defining two new random variables. We know that functions of random variables are also random variables, so X and Y are two new random variables. Uh, so it's like the joint PDF of X and Y's, whatever they gave at the bottom. Should I remember this? Good question. Even I wonder sometimes. Uh, like if you try solving questions, you could see. I don't know. I mean, it's not that difficult, maybe because it's like you have aspects of the normal distribution. How does normal distribution look like? You will have 1 by sigma root 2 pi into e power minus half x minus mu by sigma whole square, right? So you have similar terms. The only thing that's Strange is that probably you have this strange looking X and Y, and then you have the row all over the place. Row is appearing all over the place. Uh, I think that's the only difference. That is fine though. It shouldn't be difficult to remember. So that's why I said bivariate normal distribution is interesting. You have all these kinds of things, but sometimes solving the problem is easier if you if you remember that something is there. Okay, we'll see. Maybe we'll just there's nothing much to do here. X is there, Y is there. They gave the PDF. We are not deriving what it is. Maybe the interesting part is probably its properties. We'll see. But just try to keep this in mind. Let me also see. X is sigma x z1 plus mu x. Okay. Y is sigma y rho z1 plus under root 1 minus rho square z2 plus mu y. Okay. Fine. So what is the PDF? Rho, okay, you have 1 minus rho square under. Hmm. Okay, I think I remember now. We'll just see. Like I just tried to keep this in my head, but we'll see. I might have to go through this formula before the exam, but I don't think I'll remember it up until the math exam. But we'll see. Any properties? There are so many properties, so we will see. So this is the notation. So x comma y belong to the probability distribution BVN, where BVN is basically bivariate normal distribution. So there are five parameters, which is nothing but mu x, mu y, sigma square y, and rho. Five parameters. Binomial has two parameters. Multinomial has how many parameters does multinomial have? Multinomial has like two parameters, n and binomial is like n and p, but multinomial is you have n, but you have p1, p2, p3, so on till pk. So it's like a vector, or else you can treat them as individual parameters. It doesn't matter. So okay, fine. Uh, you have five parameters. Okay, fine. This is BVN. Okay, nice joint probability distribution of x and y. Fine. X and y you have to remember. X is nothing but sigma x z1 plus mu y, and okay, wait, let me just come back. Okay. X was what was X? Sigma x z1 plus mu x, and what was y1? Sigma y uh, sigma y rho square z1 plus 1 minus rho square z2 plus mu y, something like that. Let me see. Okay, there's no square. Okay, fine. So y is sigma y rho z1 plus under root 1 minus rho square z2 plus mu. Okay, fine. So careful. So if you forget, I don't know. It shouldn't cause much problem, I think, because I think the last question is on the properties of bivariate normal distribution. Because there are many properties, so we'll see. Okay, another way of writing this. Fine, but you might, I don't know, I might not know how to use this. If you take the determinant of this, what will you get? Okay, let's not get into the second part. We know there are five parameters: mu x, mu y, sigma square x, sigma square y, and rho. Rho is the correlation coefficient, right, of x and y. Since it is a function of two variables, the graph will take this 3D form. Nice. If it's a function of one variable, you can just represent it in 2D Cartesian plane. But if it's a function of two variables, then you will need a 3D graph. So you have 3D graphs. Okay, theorem. So we have properties, theorems, and so on. If x and y have a joint distribution with joint PDF given by equation 5, which is okay, which is the BVN PDF, joint PDF. So okay, so what do we have? So basically x and y belong to this bvn. Okay, then there exist two independent standard normal random variables z1 and z2. Okay, nice. Because now we remember what is x1 and we remember what is x and y, right? X is sigma x z1 plus mu x, and y is nothing but sigma y. And in the brackets, we have rho z1 plus under root 1 minus rho square into z2, and outside the brackets plus mu y. So if we can represent x and y in this form, we can find what is z1 and z2, and we can say Z1 and Z2 follow standard normal distribution, and Z1 and Z2 are independent. So that is one theorem. Okay, fine. I mean, previously we started from Z1 and Z2. Here we are starting from X and Y and then coming to Z1 and Z2. And marginal distribution of X is a normal distribution. Okay, yes. So here X and Y, both of them are normal random variables. So X will have mean mu X and variance sigma square X. Y will is the same thing. So you have the same story, mu y and sigma square y. So that is what I'm telling you. So x and y are two random normal random variables. If you find them in a joint distribution function, it becomes a bivariate normal distribution. So you could have some just x and y. You can have it, but then we are trying to represent it in terms of z1 and z2 because z1 and z2 are two independent uh, standard normal random variables. It's like some Z1, Z2 exist. We are not looking at the proof, but some Z1 and Z2 exist. Or else if you have Z1 and Z2, you can construct X and Y. That is also there. You can do that. Correlation between X and Y is rho. Yes, that is also fine. We are not proving anything. Marginal PDF of X. We just saw that X is normal random variable, right? With mean as mu X and variance as X sigma square X. So simple. It's fine. Doable. We know it is. Okay, wait. What are they doing? What is simple? What did I say simple? Yes, this one. So this is what I'm trying to tell you. So we know x is a normal random variable, right? So it belongs to normal probability distribution with mean mu x and variance sigma square x. That is fine. So and normal. I mean, see, mean is mu x, variance is sigma square x. There's nothing much here. Like if you want like the real way to do is integrate and check, like how, right, marginal means you if you want to find the marginal of x, you integrate it with respect to y across its entire range minus infinity to infinity. But we don't have to do that. They already did it for us. So the result is this: x is a normal random variable with mean mu x and variance sigma square x. So it's like considering all of this only, they gave such a complicated form previously with all the details mu x, mu y, sigma square y, rho. Like they made everything such that all of these parameters are visible in the PDF equation. Okay, anyways, it's the same story for y. Marginal of y is also the same thing. Okay, so normal random, we know how to write normal random variable. PDF, we know how to write. Fine. More properties, any more properties? Covariance of x and y, correlation of x and y. Okay. Prove that if, I mean, okay, fine. There's nothing here. It's just that if x and y belong to the probability distribution BVN, where the five parameters are there, remember the order, no? Just remember the order because the exam, they'll just give you numbers. So maybe then you'll have to know, okay, first one is mu x, second one is mu y, third one is variance of x, fourth one is variance of y, last one is correlation of x and y. So in that case, covariance is nothing but the last. Okay, what is covariance? Correlation is covariance by standard deviation into standard deviation, right? So covariance will then be uh, correlation into standard deviation of x into standard deviation of y. We are just rearranging the formula. There's nothing to prove here. Uh, okay, like in the slides, it's like this because initially we did not consider mu x to be the mean of x. and we did not consider anything. We just considered them to be constants, and slowly we are proving that mu x is indeed the uh, mean of x, and sigma square x is indeed the variance of x, and rho is indeed the correlation coefficient of x and y. But here, since we already know what is the answer, we are not going through the story that the slides is presenting to us. So there's nothing to prove here. Just to move on. So we know sigma is okay. I mean, we know that rho is a correlation coefficient, right? Okay. New theorem. Linear combination of bivariate normal random variables. Suppose two random variables x and y have a bivariate normal distribution. Okay, so x comma y belongs to some bivariate normal distribution. We know the parameters: mu x, mu y, sigma square y, and then rho. Okay, then ax plus by. Okay, now we are scaling them up and adding these two random variables. So there's this theorem. What is this saying? Ax plus by has the normal distribution with mean a mu x plus b mu y and variance a square. Okay, we have something. So see, let's say I have not z. Let me just take w probably ax plus by. Now, what is the mean of w? It's nothing but a expectation of x plus expectation of y, right? Expectation of x is mu x because I we know that x and y follows a bivariate normal distribution with parameters mu x, mu y, sigma square y, and then rho. This is a nice rho. Okay, so this is mu x and this is mu y. Then what is the variance of w? Variance of w is variance of ax plus by, and this is nothing but a square variance of x plus b square variance of y. X and y are not they need not be independent, so you'll get this extra term. The extra term is plus 2 times covariance of x comma y. Variance of x is, we know it is sigma square x. Variance of y, we know it is sigma square y, plus 2 times covariance. We've just seen that covariance is nothing but correlation into the standard deviations of x and y. So the theorem is telling that this will follow normal distribution. This will follow normal distribution with mean whatever we got. We got some mean, right? And variance whatever we got. That's it. So it is a theorem. So if you have see in bivariate normal, we know that x and y are normal themselves, and we know that if we uh, add or subtract two normal random variables, you will still get a normal random variable. That's why this w is also a normal random variable. There is nothing new in this. There's nothing new that the theorem is telling. In bivariate normal distribution, we know that x and y, like x follows normal distribution, y also follows normal distribution. So consequently, ax plus by will also follow normal distribution, and the mean and variance we just found out. So there is nothing new that. Oh my goodness, I forgot a and b. A and b. Sorry. Here a and b, no. Covariance of ax and covariance of ax. See here, what happened is variance of ax, variance of ay, covariance of ax, covariance of ay. So in covariance, if you have okay, I should tell you how to do this then. 1 minute. I'll tell you how did we get to. There is one thing in covariance. I will just show you. Okay, wait. A, B, rho. Uh, this one. Standard deviations. Fine. Then, okay, if you have a covariance of, let's say, ax plus b and cy plus d. Let's say you have some expression like this, covariance of something. Now, how do I open this? How do I open this? It's like it's just like this. So I'll just show you something. Uh, However you want to make sense of it, you make sense of it. I'll just show you something. So I will just do this ax and this one. So this is nothing but uh, how do I write this? Okay, fine. I will write it, but however you want to make sense of it, you make sense of it. So this will be a. Okay, I'll write it covariance AXCY plus covariance AX. Is this how it's going to be? Okay, I'll just get back to you later. I will just look into this. There's something about that, but we have to find what is this. I'll just write this here. If you have to know how to handle these kinds of cases, or let's say you have the capital letters are random variables, so you'll have to see how do I open this. There is something. There is a way to open this. We'll come back to that. But this is fine. There is nothing that this theorem is telling us, like nothing new about it. Fine, I'll just move on. Move on, move on, move on, move on. Conditional PDF x given y. So we're still in bivariate normal, right? So x comma y is following some bivariate normal distribution. Now x given y is another random variable. So what does x given y follow? Which distribution does x given y follow? So x given y follows normal distribution, but its mean and variance they look strange, and there is no other way out of this than remembering this, unless you want to derive everything in the exam. So this is how it's going to look like. So x given y is another random variable. If you solve the equations, you get a result which looks like this in the box. So x given y, I mean given y in the sense capital X given y is equal to small y. So it's like this is one random variable now. We know that capital Y is small y. So given this piece of information, what is the probability distribution of capital X? So this is one new random variable. X given y equal to y is one new random variable. If you solve the equations, we can find that this follows normal distribution with mean this one and variance that one. It's in front of your eyes. No other way out of this than remembering this. So I think even in the tutorials we solved some questions using this formula directly. Directly in the sense we had to find what was mu x. We had to find some cases what was sigma. It depends in the question. They'll give you incomplete information. You're supposed to figure the other pieces of information by yourself. So depending on the question. But this is the distribution. This is how x given y looks like. So how do you remember this? No other way. So mu x plus rho sigma x plus okay fine. Nice. I rho into sigma x by sigma y minus mu y. Okay, fine. Nice. No other way out of this. Fine. Uh, this is the distribution of the conditional random variable. Basically, x given y. If it's y given x, then you just interchange the things. That's it. Instead of x, y will be there if y is there. Okay, okay, they've done it for us. Y given x. Fine. They interchange it for us. Nice. So it's like the slides and I, we are on the same page somehow. I mean, even technically, we are on the same page. Okay, graph. I mean, they're not asking you to plot any graph, so fine, interesting graph. Uh, More results. Okay, we are looking for results because we'll be using the properties often, I think. If x comma y is bivariate normal, if it follows bivariate normal distribution, then the marginal and conditional are all univariate normal. Yes, so we've seen x is normal, y is normal, x given y is normal, y given x is normal. So they're all normal. Univariate normal in the sense so there's only one variable in that case. Now you might wonder, x given y, there are two variables, right? How is it univariate? There, y is no longer a variable because you're already giving y, small y, a value. So the only variable in x given y is x. The only variable in y given x is y. So that is why it's univariate. So you just have to use your normal distribution, which we went through long ago, or yesterday, not very long ago. Okay, they're all normal, and we know we've seen what is uh, they're all normal. Now, what is the additional information that you require? What is the mean? What is the variance? For x, it is mu x and sigma square x. For y, it is mu y and sigma square y. For x given y, you just saw x given y. What is the mean of x given y? It is mu x plus rho sigma x by sigma y into y minus mu y. Variance was sigma x square into 1 minus rho square. The opposite is the case for y given x. Okay, that is one theorem. Nice. We saw. We know they're all normal. Okay, what is theorem 12? If x comma y follows a bivariate normal distribution, okay, now there's a theorem about independence. Then x and y are independent if and only if rho is 0. Okay, now what is rho? Rho is the correlation coefficient. What does it describe? It describes the linear relationship between x and y. I'm talking in general. In general, rho represents the uh, linear relationship between x and y. So if rho is 0, it means x and y do not have linear relationship. But it doesn't mean they're independent because there could be non-linear relationship, right? When I say y is equal to x square, in that case x and y have a non-linear relationship, but they have no linear relationship. In that case, rho is 0, but it doesn't mean x and y are independent. They are just uncorrelated. So if rho is 0, it means uncorrelated. If rho is non-zero, they're correlated. But here, theorem 12 is stating that x and y are independent if and only if rho is 0. So it is stating that if rho is 0, then they're independent. So if they're not linearly dependent, they are non-linearly also not dependent. So this is a very case specific theorem. Why is this true? It is you can look at the proof, but okay, how do I prove it? If I show that the joint probability distribution of x and y is equal to the uh, product of the marginals of x and y, then you can say x and y are independent, right? Given that rho is 0. You can prove that. If rho is 0, then you can show, you can prove it, but they won't ask you proof questions. So you just have to remember this theorem. So if rho turns out to be 0, only in this case x and y will be independent. In general cases, if rho is 0, it just means that they don't have a linear relationship. They could have a non-linear relationship. So the only thing that is stopping this is the bivariate normal distribution. It's like it will ensure that if rho is 0, then x and y has to be independent. This bivariate normal distribution will ensure that is true. Fine. So new information, new piece of information, and vice versa also. So if x and y are independent, then rho is 0. If rho is 0, then x and y are independent. Both the ways it's true. That's why because we have if and only if. So it is a by implication. So implication goes both ways. Anyways, nice piece of information. We will not look at the proof. How to prove it? I gave you the idea. You just show that the joint probability distribution is nothing but the product of their individual marginal PDFs. Given that rho is 0. So rho is 0. That is the thing here. Rho should be 0. Fine. So if rho is 0, x and y are independent. If x and y are independent, rho is 0. in the case where x comma y is a bi x comma y follows bivariate normal distribution. Other cases it need not be the case. So see, these are some questions. See, the A question is 2x plus y. See, we know that x and y are jointly normal, or in other words, bivariate normal distribution. So we saw that ax plus by will follow normal distribution. We know how to solve problems of normal distribution. So A is very much solvable. You just have to find the new mean and new variance and solve it. Covariance. Okay, yes. So this is why I was talking about uh, that thing. I will just show you. I was talking about this for a reason. So fine. Let me. I will write something. I mean, you could verify it later. Let me write something. So here you consider the small letters to be constants and capital letters to be random variables. Uh, from what I remember, I think like these constants will not affect covariance. So I will simply write this. Constants will not constant in the sense these constants. I'm not talking about the coefficients of random variables. These constants will not affect. So basically, uh, change of origin will not affect covariance, at least from what I remember. I mean, we can go there and verify that is a different story. So it will become this. Now, how do I proceed with this? So what I'll do is I will simply do this. However you want to make sense of it, please make sense of it. But I will continue with this. Uh, Covariance of AA dt plus covariance of AAEE plus same story over here. Okay, let me keep that. Same story. So covariance BB dt plus covariance of BVEE. Okay, we did this. This was the main part. Now it's simple. So the coefficients can be written outside covariance. I'm just using the properties of covariance. We are not going to prove it because that is not the point here. We have to know how to use the properties of covariance. All of this, I think, will be found in Unit 2. If we have the time, we'll go to Unit 2, but we'll see. I think we will find the time, but we'll see. All of this will be found in Unit 2. The properties. You just have to go to covariance, correlation. There, all of this is there. All the properties are given there. So I'm just using the properties. I'm just showing you the properties that could help you in the exam. That's it. It's like we're using all the properties at the same time. So that is why it looks like this. Okay, fine. So A and D can be written outside. So A, D, covariance, A, D, A, E, covariance, A, E, B, D, covariance, B, D, B, E, covariance, B, E. Now we know how to find covariance of two random variables, right? It's simple. We know how to do this. So I showed you how to find the covariance of this complex looking thing. It just got divided into four simpler things. So similarly, like how where do you use this? If you look at this question in b bit, you have covariance of x plus y comma 2x minus y. So let us simplify this equation so that you will be able to solve it. So you have covariance of x plus y and 2x minus y, right? Did I read it right, or x plus y 2x? Okay, yes, so right. So same procedure. So what do you do? There is no extra constant, so that is fine. So what do you do? Just do this. This is equal to nothing but covariance of x comma 2x and covariance of x comma minus y plus same story for the other thing as well. Covariance of y comma 2x plus covariance of y comma minus y. Now we did the main part. Now it's just the matter of removing the constants outside. So if you remove the constants, what will you get? Covariance. Mind you, in the if you're taking variance, then this will become 2 square. But this is covariance, so the square will not come. How do I know this? Unit 2. You have to go to unit 2 and look at the properties. So this is there. So minus 1 is coming outside. So covariance x comma y. Covariance, 2 is coming outside. So plus 2 covariance y comma x. Minus is coming outside. So fine. We removed all the constants as well. I mean, we brought it outside. Now, what is covariance of x comma x? Covariance of x comma x is nothing but the variance of x. So this will be nothing but this one. How do I know? You can check the properties, or else you can. I mean, you can see for yourself. If you, it's just a property. Covariance of x comma x is nothing but this one. Uh, C. See, what is covariance of x comma y? Covariance of x comma y is nothing but expectation of xy minus expectation of x into expectation of y. So in that case, what is covariance of x comma x? It is nothing but expectation of x square minus expectation of x whole square. We know what is this. This is the variance. This is the variance of x. So that is how I know that covariance of x comma x is nothing but variance of x squared. Okay, fine. So continuing with this, so what is covariance of x and y? It is nothing but the correlation times standard deviations. We saw that because I know that correlation is nothing but covariance of x comma y divided by standard deviation of x, standard deviation of y. We also know this. From here I got my covariance. And covariance y comma x, covariance x comma y, the order doesn't matter. So minus 1 plus 2. So minus 1 plus 2 means plus 1. So you get plus here. And then minus covariance of y comma y, which is nothing but sigma y square. Done. Now it's a matter of knowing what is sigma x and what is rho xy and all of that. Is it given in the question? They gave all the parameters. They gave mu x, mu y, sigma square x, sigma square y, and the rho. So they gave all the parameters necessary for me to solve any problem about x and y. So it's just a matter of substitution now. So that is B. B is also nice. C, in C now you have to use the conditional PDF. So uh, how do you use that? How do you use that? First, you'll have to know the formula, right? What is the mean of, first of all, what is it? This is y given x. This is y given x. This is y given x equal to 2 is a random variable, and this random variable is greater than 1. Y given x equal to 2 is greater than 1. I mean, here x is a constant, so the only variable is y. That's why this greater than 1 is placed beside y, or else uh, for your maybe if you want to get not less confused, if you want to have less confusion, you can just replace y given x equal to 2 with some t. So then I can write y greater than 1 x equal to 2 as t greater than 1. I mean, this is just a matter of substitution, but it's just there to reduce the confusion, or else you can go on and just use this in your equations, or else you can simply write this, because I know that my t will now follow uh, normal distribution with mu. This is y given x, right? So mu y plus rho sigma y sigma x, uh, 2 minus mu x, and the variance will be sigma y square 1 minus rho square. So this is your new normal distribution. Now you can solve it. You know what is mean, you know what is variance. You just have to find the probability of t greater than 1. That's it. I mean, you can convert this to normal, standard normal, and then you can use the z values. You can use the z table to find the answer. So you just have to find the probability of this now. This is your z now. So you just have to find probability of z greater than 1 minus mu t by sigma t. I mean, see, using t is simple because you don't have to write y greater than 1. You don't have to write this every single time. If you replace it in the beginning, it becomes simple to write. That's it. There is no extra benefit other than just uh, relieving ourselves from the pain of having to write it again and again. Okay, nice. So this question is nice. It's like it's making us use all the properties that we've learned until now. Nice. So we've discussed enough about we've discussed enough about this example. We'll just go on. You can solve it now. I think you should be able to solve. I've told you everything, at least until now. Let's see if there is any other property that we would need. Any other property? No, it's all calculations and things. Oh, nice. Beautiful. Okay, nice, nice, beautiful. So it's here. So covariance of x comma x is nothing but variance of x. And covariance of x comma y is the same as covariance of y comma x. And you don't have to memorize any of these. I showed you how to find for anything, right? So you don't have to memorize anything. I showed you how to find it. So in one step, not one step, but in like one way. I showed you one way, and that one way encompasses all of these 6 points. So you don't have to memorize. You can do it yourself. By okay, fine, nice, enough said. This PDF is also done. So unit 5 was done, unit 3 and unit 4. Fine. So we have like 1 hour. We have like 1 hour. Do you want me to go to unit 2? I think unit 2 is simple, right? So I will just put a message. Uh, wait, I'll put. I'll just put a message in the group and okay. Someone said I could go into unit 2. So what is in unit 2? It's just the basics. Okay, let's see what is in unit 2. Mm, vector random variables, joint, marginal. Let me see. Let me just see. Where does it even start? Let's see. Is there anything that we could do? Because they're like, okay, joint. Okay, the last part, I think, after expectation. All of this is just the basics. All of you must know all of this by now, I suppose. Like they told, direct questions will not be asked from probability, mass function, density, cumulative. Like we are still indirectly using all of this, but it's like you won't get direct questions. That's it. In the sense, they won't ask you to. Uh, it's not like they'll give you a function and they'll ask you, is this a valid CDF? There won't be questions like that. Is this verify that this is a distribution? These questions won't come. Okay, I think somewhere here, I don't know. Mixed type. What is mixed type? Okay, mix is okay, fine. Continuous and discrete, right? If you mix them up, they become mixed. Okay, I think it probably begins from here because in unit 2 it says joint, marginal, and all of that. So two-dimensional random variable. Is there, see, we went through so many things. We went through bivariate normal distribution. That is a two-dimensional random variable. Yes, that is a two-dimensional random variable. What do I see in this? Uh, uh, okay, what is there to say? What is there in this? They're just showing you the notation, right? If it's discrete, you use summation. If it's continuous, you use integration, all of that. Fine. There's this notation in this. I think it's much better if we just go through the problems, or if you people just go through the problems. There's nothing much. See, all of this feels very basic after having gone through uh, all those bigger topics. Okay, you have conditional here. How to write conditional probability. So x given y is nothing but x and y divided by y. So that is there. Fine. So necessary and sufficient condition for independence. So I can write x and y as just p of x into p of y. So what does that mean? That means p of x given y is equal to p of x. If x and y are independent, p of x given y is equal to p of x because it is not dependent on y. So irrespective of whether y is given or not, p of x given y will be equal to p of x. You can verify all of that mathematically. That is fine. Uh, marginal. See, if you're taking if you're trying to find marginal PDF, you will integrate it. If you want, see, if you have a joint uh, random variable like x comma y, if you want to find the marginal of x, marginal PDF of x, what will you do? You will integrate the joint PDF with respect to y across its entire range. But let's say you want to find the marginal CDF of x. So if you want to find the marginal CDF of x, what do you do? If you have the joint CDF, you just take limit tending to infinity. That's it. So don't integrate your CDF. So if you want to find the marginal CDF of x, you have to take limit y tending to infinity. Whose limit are we supposed to take? The limit of the joint CDF. That it's given here. That's fine. Where does integration come into picture? It, in while finding PDFs or PMFs, there integration comes into picture. Or if it's discrete, you get summations. Mm, fine. Do you want me to write that separately? I don't know. Okay, let me just write it. I don't see anything that I could tell in this. So I'll just write something. So let's say this follows distribution, some distribution where I have, let's say, joint PDF as well as joint CDF. Now there are four things that I could find: the marginal CDF, PDF of X and Y. So we have four things. So how do I find the marginal? I'm assuming they're all continuous. If it's discrete, so if it's discrete, then you get summation instead of integration. That's it. And I'm assuming X is X and Y are lying here. It can, okay, fine. Or else you can take any other interval. You can put A, B, C, D. A, B, C, D. It's fine. This is given. Fine. So how do I find the marginal of X? There are two ways, no? You can, depending on what is given, you can simply do this. Integrate fxy with respect to y because you want marginal of y, marginal of x across the range of y. So y is ranging from C to D. This is if a PDF is given, or else if a CDF is given, what do you do? If CDF is given, then it's the same story, but what is going to happen is, I'll just write it once again. You just differentiate your CDF to get your PDF, and then it's the same story. This is your PDF now. You integrate it. You'll get your marginal of x. Same as the story with marginal of y. So how is it the same story? How is it the same story? So if you want to find okay, when I say differentiate, now with what will you differentiate? With respect to x or y? That will be a good question, no? So let me read it. Fine. So if you have a joint CDF, it's a function of two random variables. Now, with respect to what will you differentiate? With respect to x or with respect to y? That's a good question, no? So it's like dou by dou something x or y of xy, x comma y, dy. That is fine. So here what will come? Will x come or will y come? You want the PDF of x. That is uh, okay. Got it. So here what you're supposed to do is you're supposed to do this. Yes. So I'll show you. Let's see. I think you're supposed to do that. Let's see if that is there somewhere. Is it there somewhere? Conditional will come back to you. Conditional. Where is it? No, not there. Like the question is, you have the CDF, now you want to find the PDF. So what do you do? Let me just verify because it seems, because if it appears, you should not be confused. You should be able to solve it. Should not get stuck like me, like how I'm stuck right now. Fine, let me just verify this. Uh, PDF of joint CDF. Yes, so fine, this is right. So what did we do? We have to differentiate with respect to both x and y. This corresponds to fxy is the same story, but if PDF is not directly given, if only CDF is given, this is how you find the PDF. Anyways, nice. Now let's say I said same story with y, no? So if y is there, what will happen? So if you want to find the marginal PDF of y, then you will integrate it with respect to x, and x is ranging from a to b. That is when PDF is given. What if PDF is not given? What if CDF is given? If CDF is given, then find the PDF. How do you find the PDF? You find PDF this way. This is your PDF. You have to differentiate your joint CDF function. So this is your PDF. Same story. Now integrate with respect to x across its entire range. So this is how you find uh, marginal density of x and y. Marginal PDFs of x and y. So let's say now you want to find the marginal CDF of x. How do you find marginal CDF of x? Let's say you have the joint PDF. From joint PDF, how will you get marginal PDF of x, CDF of x? So we'll see. Let's say, okay, first we'll take the case where we have marginal CDF, which is this one. Let's say we have marginal CDF. So what did I tell you? If you're finding marginal CDF of x, you just have to take limit y tends to infinity. So limit y tends to infinity. Whose limit are we taking? We're taking the limit of the joint CDF. So this will give you the marginal of x. Now suppose you don't have the joint CDF. Let's say you have the joint PDF. Then what are we supposed to do? If that is the case, then find the joint CDF. How to find the joint CDF from PDF? If PDF is given, uh, okay, let me just write it like this. If PDF is, you still have to take limit y tends to infinity. It means now from your PDF you have to find CDF. How do we do that? You'll have to integrate your PDF twice. First with respect to let's say dx and okay, let me just say, and then dy. X is ranging from a to b, y is ranging from c to d. This is nothing but your CDF. This is nothing but your CDF. So if CDF is given directly, you can do this. If CDF is not given, then find the CDF and then put the limits. Same is the case with see now all of these are just variables now. If they're in numbers, probably it will be easier for you to digest or whatever. I'm just showing you different cases because I don't see anything else that I could tell in this segment. So let's say you want to find the marginal CDF of y, then what will change? If you want to find the marginal CDF of y, if you have the joint CDF, just put x tending to infinity there. If you don't have the joint CDF, let's say you have the joint PDF, then find the joint CDF. Yeah, this is how you find the joint CDF and take extend into infinity. That's it. Extends to infinity. Uh, nice. So four possible questions. I mean, I'm not telling that these are, I mean, I'm not telling that one of these will come in the exam. I'm just telling you because I saw joint, what is this? Joint margin in the portion. Maybe I think more stress will be on unit 4 and 5 because it is new. I think. I'm just thinking. My channel's name is Free Thinker. I'm free to think whatever I want. Fine. So I found this interesting. That was in the continuous case that I've been discussing. If it's discrete, then instead of integration, you'll have summation. Look something like this. Fine. Mm, I saw some interesting things like conditional something. Conditional. See, conditional. Didn't we come across this? This is conditional for joint, right? I mean, is okay. What is the probability of x given y? It's nothing but probability of x and y divided by probability of y. Fine. No, I think okay. We came here. We came across this. Was this here? Is this here? Yes. So it is here only. This is the same. If C and D can be like C can be minus infinity, D can be plus infinity. That is fine. I covered all the cases. I don't see all of them are here. I mean, except at least for the continuous case. Uh, why does it look like I got stuck somewhere? It looks like my live video got stuck. Am I still live? Yes, but what is this? Okay, fine. Let me just join the meeting back. It got stuck, I think. Okay. I think it's like we almost covered everything. There's nothing new here. We'll just go on then. So what was next in unit 2? Marginal, okay. So joint, okay. Marginal, fine. I think you get the idea, right? Joint is like you have more than one variable. And together they follow some distribution. Oh no, we're not talking about distributions. Together they have some PDF, CDF, and so on. Okay, we have. since distribution, since joint distribution is a part of the syllabus, look at this properties of joint distribution. Since this is a part of syllabus, they could ask you this, maybe. How can we forget this? The first property is very, very much interesting. So look at the first property. It's like probability of x lying in between a1 and b1, and the probability of y lying in between a2 and b2 is given as this one. So how do we how does this happen? It's just that if you get the idea, you wouldn't have to memorize. The idea is this: if you have, let's say, this is x1 and this is x2. I said x1 lies in between a1 and b1, and x2 lies in between a2 and b2. It would mean I'll have to I have to find the probability that my x1 comma x2 lies in this region, right? How do I do that? First, I'll just mark the points and maybe it will start making sense. This is a1 comma a2. This is b1 comma a2. This is a1 comma b2. This is a2 comma b2. So how do I get this? I have to express this in terms of CDF because fine. So okay, let me write. If I write CDF of A2 comma B2, what will I get? If I write this, it means it's representing the entire square. Like, what is CDF? CDF A2 comma B2 means x1 is wait. I'll just write. What does this mean? This is nothing but probability of x1 less than or equal to a2, and probability of x2 less than or equal to b2. Oh, sorry, this is b1, b2, b1, b2, b1, a2, a1, a2, a1, b2. Fine. So this would mean x1 will take all the values before, sorry, this is b1, and x2 will take all the values before b2. So that is the entire square. But I only want the red square. So what do I do? I subtract something. What do I subtract? Okay, I will say this is 1. So this blue box is 1. I'll need one more box. So I will write, I'll make a second box. So f of fxy, uh, b1 a2. Now which box will which rectangle is going to represent this? What does it mean? So x1 goes until b1, x1 goes until b1, and then x2 x1 goes until b1 and x2 goes until a2. So it would mean the lower rectangle. So this lower rectangle is area 2. And what does fxy? I'm just writing the CDFs of these 4 points. CDF at these 4 points. A1, A2. What would that mean? A1, B2 or A1, A2. I'll write A1, B2 first. What does this do? X1 goes until A1 and X2 goes until B2. So this rectangle. This rectangle is rectangle 3. What is the last rectangle? The last rectangle is fxy a1 a2. It's the smaller rectangle, the smallest. This rectangle, it goes until a1 and it goes until a2. So this is my rectangle 4. So I can obtain the red region by doing this. What do I do? So I'll do 1 rectangle 1, which is a bigger rectangle, minus rectangle 2 minus rectangle 3. That means what happened? I have this bigger rectangle. I subtracted, I have 4 regions, right? I subtracted, what did I subtract from this? I subtracted 2, I subtracted 3, but this bottom portion got subtracted twice. So I'll have to add this box again so that only each of the boxes is subtracted once. So I will add box 4. So this is the idea behind writing probability of x lying in between. Uh, where is it lying in between? A1 and B1, no? A1 and B1, comma, uh, what else? A1, B1, A2, B2. A2 is x1, right? A2, B2. This is nothing but 1 minus 2 minus 3 plus 1. So basically, CDF of the largest point, I mean, largest in the sense, farthest point, minus fxy. So once it's A1, B2, the other time it is, is it A1, A1, B2? And B1, A2. And once you add the smaller box, so fxy, A1, A2. So that is the idea behind this formula. That is how you got property A. And what is property B? Property B is CDF minus infinity y. What does minus infinity y mean? So it means, okay, they didn't use x1, x2, they directly used xy, so that is fine. So in my case, x1 will be x and x2 will be y, that is fine. CDF of minus infinity y, what does that mean? It means your x is at minus infinity. If your x is at minus infinity, it means you are not starting anything. You're nowhere. You are nowhere. You are like you're somewhere over there. It's like you didn't even start coming, because coming in the sense you want to go from left to right. You want to go this way. If your x is at minus infinity, it means you never arrived. In that sense, if you've never come, your whatever is the probability, it's going to be zero. Like in that sense, I mean, how do I say? I mean, if for the single variable case, you do remember, right? If x is tending to infinity, CDF of x will be 0, minus infinity. You know this, right? Uh, limit x tending to minus infinity, this is 0. And limit x tending to infinity, CDF is going to be 1. So it's the same idea. Now, instead of one variable, we have two variables. That's it. So if any one of these values is like minus infinity, then it's going to be 0. That is what they've written here. F of minus infinity comma y, that will be 0. F of x comma minus infinity will also be 0. And f of f of infinity comma infinity should be 1, not f of minus infinity comma infinity. That is not right, because where is minus infinity comma infinity? Minus infinity comma infinity is, it's still somewhere over there. You should not be at minus infinity. Your probability will be 1 if it is like you're going in this direction. You should go in infinity comma infinity direction. Any other direction is like, no, it's still 0. So this is not supposed to be 1. This is not 1. Or else this should not be minus. F of infinity comma infinity is 1. That is fine. uh, Marginal. We've looked at all possible cases. I think we made an error somewhere. Let me see. Let me see. CDF, no, PDF, marginal PDF of X. You integrate across Y. Fine. This is also fine. Marginal PDF of Y. This that will also be fine. CDF of X. I mean, instead of doing this, you can directly do this. So what you can do here is, if you have access to the PDF, you can directly do something, and that is, first you integrate across Y. First you integrate across Y. Integrate across Y. So what will this be? Y ranges from C to D. I mean, you could have done the previous thing as well, but the idea here is, now you integrate it from, where is X? X is lying from A to B. So now you will integrate it from A to X. This will be sufficient. You don't have to integrate from A to and okay, fine. So here infinity also is not required, because the maximum value y can take is D. So y should tend to D. That okay, that is the thing here. So y should tend to D. Nice. So one more correction. So x will tend to B. You don't have to do this, because there is a simpler way, which is simpler in the sense, I mean, you will eventually do this, but it's like you don't have to do extra work. That's it. It's the same thing, but you're not doing extra work here. So how do I find marginal CDF of y? If I have the joint PDF, I'm integrating it with respect to x across the entire range of x. Then I'm integrating with respect to y from the least value to the current value, which is y. This will give me the CDF of y, marginal CDF. Fine, nice. We don't have to find this one, because we can directly find using the integration. Because what is integration? Integration of PDF will give you CDF. So that is essentially what is happening. And differentiation of CDF will give you PDF. Fine, nice. So this is like a nice little summary, I think, for the continuous case at least. Discrete case, there'll be summations. There's nothing to remember other than the fact that if you differentiate CDF, you get PDF. If you integrate PDF, you get CDF. But here the integration and differentiation, we're doing it two times, because we have two variables. Okay, we are roaming here and there for the past few minutes. Okay, fine. Even the other thing will get over now. What is the other thing? Conditional joint expectation, conditional expectation. Okay, that this is question two, right? I just forgot units represented the questions. So why is this happening? Shh. Let me just open something. What was after this? This one. Joint expectation, conditional expectation. We just, I mean, it was in the, oh, it's right in front of me. My bad. But joint expectation, I think it was in the previous slide. We've seen it. Fine. No, but they won't ask you direct questions about expectations. So, because they're like mathematical expectation, variance, standard deviation, MGF out of syllabus. But you get the idea. You know how to find expectation. This is the expectation formula. In case you forget the expectation of anything, you're very much free to use the formula to derive the thing in the exam. That's only in the worst case if you forgot, if you forget any of the expectations. Fine. Uh, Expectation of a function. I mean, they won't ask you direct questions. We've been using expectation all this time. So, and yes, so if this is also nice expectation x y x and y are independent, I can split them into the product. Very similar to the probability, right? When if two events A and B are independent, probability of A and B will be nothing but probability of A into probability of B. Excuse me. Variance out of syllabus, but it doesn't make it a stranger. We've been using variance expectation all this time. See some properties of variance. So we've been using some properties of variance as well. So if x and y are independent, then variance of x plus y or variance of x minus y doesn't matter. It is nothing but variance of x plus variance of y. We need more properties. There are more properties. Uh, where I think it will be later. There are more properties to variance. Like if there's a constant, variance of ax will be a square variance of x. And if x and y are not independent, then you will get something called covariance. So okay, maybe when covariance is introduced, we will look at more. Okay, see here, variance of ax plus b is a square variance of x. So it means variance is affected by scaling, but it's not affected by change of origin. So b is just going to disappear. Okay. Even in covariance, that's happening, no? So we'll just come to covariance. Even this moments is out of syllabus. Variance for joint distributions. Joint distribution is a part of syllabus, so this is also a part of syllabus. I mean, they didn't explicitly mention the variance. They're like conditional probability, independence, joint expectation, and conditional expectation. Will it come after this, or did we cross it? Because expectation comes before, right? Okay, we'll just go on. Let's see. Just see. Okay, wait. Let me just see. What did I come across? Maybe it comes later. It's not here. What is not here? I was searching for what is here? Joint expectations. I saw that somewhere. But before joint expectation, we got joint variance. Okay, so that is called covariance. Fine. So variance of joint distribution is covariance. Nice. See the definition. So what is the definition? Expectation of x minus mu x into y minus mu y. So finally, it will become expectation of x into expectation of y minus. No, no, it will become expectation of xy minus expectation of x into expectation of y. Only if they are independent, then covariance becomes zero. That is nice. Independent in the sense like independent. It need not be just linearly independent. because when I'm talking about linear independence, then correlation coefficient comes into picture. That will only capture linear relationships. It will not capture any other relationships. But here we are talking about independence. So correlation is a different thing. Independence is a different thing. If two random variables are independent, then those two random variables will be uncorrelated. But the vice versa need not be true. Just because rho is zero, it need not mean that the random variables are independent. But in the case of bivariate normal distribution, if rho is zero, then x and y will surely be independent. That's a theorem. So that's a case specific. Okay, properties. Properties. So if you're finding covariance, the coefficients of the random variables will just come outside. So AB covariance xy. We use this, right? We use this property. Covariance of x plus a, y plus b. A and b will not affect it, so it will. You can just ignore that. Become covariance of x comma y. We've seen that. Here also something similar is happening. It's like the coefficient of x is 1 by sigma x, so that came outside. Coefficient of y is 1 by sigma y, that also came outside. The other is a constant, so you can simply ignore that. That's not going to affect us. And okay, if you notice this, what is covariance of x comma y divided by sigma x sigma y? This is nothing but the correlation, right? Correlation is defined this way. I mean, we didn't come across correlation yet, but this is like foreshadowing. There is correlation right here, right in front of your eyes, but it's not yet revealed to be correlation. Fine, variance. Yes, so here xi's are not independent, so you will get this extra term. If they're independent, then it's simply a1 square variance of x1 plus a2 square variance of x2. But here you have this extra term. But is this even in syllabus? I mean, it's just a property, so I just stopped here. Or there's nothing special about this slide, just a property. Right? I'm waiting for a joint expectation. Where is, okay, at least, okay, conditional expectation. These are just some properties. We've been using most of them, so I just stopped here for a while. Especially the last property of variance. We used this in uh, bivariate normal, right? We use this because their x and y are not need not be independent. So you'll get variance of x1 plus variance of x2 plus 2 times covariance. We saw this in bivariate normal distribution. Okay, conditional expectation is explicitly mentioned in the syllabus, so I'm just going through this. What is conditional expectation? You want to find the expectation of y given x equal to x. So just apply the definition. So your variable here is y. So and your probability density function is going to be f of y given x. That's it. Simple. Just apply expectation formula. This is a continuous case. If it's discrete, then you have a summation. Joint expectation. Joint expectation is there a separate slide for that? Let me just see, or else I'll just write it for you. Simple, simple idea. Skewness. It's not in the syllabus because they've not mentioned anything about it, so I'll not be looking at this. But it's simple. It's just third moment by sigma q, but we are not going to through it. Fourth moment by sigma bar 4 is fine. I don't see it in the syllabus though. Correlation. Okay, yes. So correlation is just going to uh, talk about correlation between two random variables is just the measure of the linear. How much is the linear relationship? So if correlation is zero, it means there is no linear relationship, but it doesn't mean they are independent. They could have non-linear relationship and therefore be dependent. So if rho is zero, it means they're uncorrelated. That's it. I'm telling this again, but in bivariate normal distribution, if rho is zero, then you can declare that the two random variables are uh, independent. Okay, so correlation coefficient is defined to be covariance divided by the product of standard deviations of x and y. Nice. And it will always lie in between -1 and 1. This is a part of the syllabus. Covariance and correlation coefficient. How do I know it always lies in between -1 and 1? Because of this relation. Where is it? Where is it? No, I don't want to go up now. Where is it? Where is it? Yes, here. So there is one property. So mod sigma xy is less than or equal to sigma x sigma y. I do not know the reason, but from here we can show that covariance lies in between -1 and 1. Not covariance, correlation lies in between -1 and 1. Just shift, like take this into the denominator, open the mod, then you can see that correlation lies in between -1 and 1 using the last relation. That is a, I do not know where did that come from. But okay, fine. I didn't think about it. Hmm, okay, correlation, linear relationship basically, -1 to 1. Like what is positive correlation? It's like if x increases, y also increases. What is negative correlation? If x increases, y decreases. Something like that. Fine. So you can look at it. If x increases, y increases. Here, if x increases, y decreases. So negative correlation. Here, if x increases, nothing is happening to y. So zero. Correlation is zero. But they're all linear relationships. So linear. So properties of correlation. What is happening? Independent of change of scale and okay, okay, interesting. So correlation of A plus H mu and B plus KV. Oh, what did it turn out to be? It turned out to be HK covariance UV. Okay, nice. So this is one property. Correlation. The rho basically. Rho is independent of change of scale and origin. So they took U as x minus a by h and v as y minus b by k, and they tried to find the correlation of u and v. Given that we know the correlation of x and no, no, I think it's the opposite. We know the correlation of no, what is given, what is not given here. Whatever it is, yeah. Just think either x y, either that correlation is given or this whatever is given. Uh, I think correlation of u and v is given. I think, and we want to find correlation of x and y, something like that. Fine. Finally, okay. There's nothing much here. Nothing much in the sense there is one piece of information that is correlation is independent of change of scale and origin. Covariance is independent of change of origin, but change of scale does affect covariance. Uh, Now, did we assume anything here? Okay, here we assumed h and k to be positive constants. If they are not positive, then you have this. You have this. So okay, so there is some change. There is some change. So Correlation is independent of change of scale and origin only if the coefficients of x and y are positive, or else you have this relation. What is the relation? Correlation of ax plus b and cy plus d is nothing but correlation of x and y is still there, but then it depends on the constants now. Which constants? The coefficients of x and y. So AC by mod AC. Nice. So this is the general property. So I've been telling the same thing again and again, right? It's in this box. So uncorrelated means rho is zero. Rho is zero means there is no linear relationship, but it doesn't mean they're not dependent on each other. They could have a non-linear relationship. For example, y equal to x squared. That is in the pink box here. If they're independent, then they're obviously uncorrelated. Independent means no form of relationship. So even linear won't be there. So rho is zero. But if rho is zero, it doesn't mean they're independent. But in the bivariate normal distribution, if rho is zero, then x and y are independent. That is a different. That's a very case specific example. Okay, example. Are there any other things for me to see in this? Thank you. Okay, that means unit 2 is also done. Unit 2 is also done. Now, what is remaining? Unit 1. I think you can go through it. There's counting techniques, permutations, combinations, sample space, events, conditional probability, independence of events, theorem of total probability, Bayes theorem. I mean, you just go through them. Let me just open the PPT. Let me see if there's anything for me to look at. It should be in this PPT. There's only one PPT left, and I suppose there should be at least 100. Okay, 59. Okay, okay. Uh, oh, I've seen this slide. Like it's been a long time since I've seen these slides. What do we have here? Counting techniques. I mean, counting techniques, permutation, combinations. I think all of you know. There's nothing for me to tell how to count. We had this in DMS last time, like counting technique. How do we count? How to count? So I don't. So permutations is like the number of ways in which you can linearly arrange uh, k number of distinct objects from n number of distinct objects, something like that. They're all distinct objects, so that one you have to keep in mind. So linearly you're arranging. Combinations is like the number of selections. You want to select k number of distinct objects from n number of distinct objects. So the number of ways in which you can do that is nck. And how are we doing the selections and things without repetition? It's like after you pick it, you can't pick it once more. So distinct objects without repetition. Nice. Now this is becoming a DMS class at this point. Mm, axiomatic definition of probability. So this is classical probability. So we won't be using this. We'll go on to the axiomatic. See, classical probability is the basic probability. We won't be using this. We'll be using the axiomatic. Statistical is fine. That is empirical. It's like it's based on the experiment. But we'll go to the axiomatic uh, definition of probability. Okay, before that, circular permutation. Previous one was linear permutation. This is circular permutation. Okay, so in a circle, it's let's say you want to uh, let's say you have n places and n things. In how many ways can you arrange them in a circle? It will be n minus 1 factorial. Reasons and all you can think about it later, but the answer is n minus 1 factorial. And let's say you're making a garland. The speciality about a garland is if you flip it by 180 degrees, it's still the same garland. You don't get any difference. So now what you're supposed to do, you're supposed to divide it by 2. So in that case, it will be n minus 1 factorial by 2. So they've given bracelet, garland, whatever. So circular permutations. Fine. But if you're sitting in a table, in a round table, you can't flip yourselves by 180 degrees, right? That's meaningless. So it's still n minus 1 factorial. But in cases like when you're making a bracelet, necklace, garland, all these cases, you have to divide n minus 1 factorial by 2. Okay, sample space. The counting techniques you can just see. I have nothing to tell. I just went through permutation, combination. I'm waiting for axiomatic definition of probability. Did we skip it? Or is it coming? I have no idea. Let me just see once. Where is axiomatic definition of probability? I should have seen axiomatic. I don't remember seeing, so I would like to assume it's in the slides that follow. Where is axiomatic? I've seen classical. It can't get shorter. Fine. This is classical. There was empirical as well. Where is axiomatic? Okay, fine. So axiomatic will come much later on. So we'll just wait for that. So after circular permutation, here what did they put? Sample space. So sample space is just the set of all possible outcomes. That's it. And what do I mean by set? Set is a collection of unique objects. So you won't have two events that represent. You wouldn't have two elements representing the same event. So nice. No two or more of them can occur simultaneously. If they're occurring simultaneously, then it's still a part of the same event. That's why you can't say A and B are two different events and let them occur simultaneously. If they're occurring simultaneously, it's the same event. Okay, nice. And exactly one of the outcomes was that. Okay, fine. So set of all possible outcomes. Each element denotes a possible outcome. Yes, of course, you can't have an impossible outcome in the set. Any trial is a result. Any trial results in an outcome that corresponds to one and only one element of the set S. Okay, so let's say I have my sample space and I perform a trial. Then the trial must correspond to only one event. It shouldn't be mapped to uh, multiple events of the sample space. It's like my sample space of rolling a die. What is it? I'll get 1, 2, 3, 4, 5, 6. So if I roll a die, I I will only get uh, one correspondence. It's like I will either get 1, 2, 3, 4, 5, or 6. I won't get 4 and 6 at the same time, right? So that's it. Uh, Enough of theory. Sample space, finite, infinite. Okay, discrete. So discrete sample space can have infinitely many points, but I mean, if it's countably infinite, it's fine. What do you mean by countably infinite? I can count it 1, 2, 3, 4. Like there's a bijection between the set of natural numbers and the sample space. If that is there, that means the set is countably infinite. If it's uncountable, then it's probably not discrete. It's continuous in that case. Yes, so non-denumerable. Uh, you can read the theory, but I will not just go on. This is nothing. It's already 1 p.m. Complement, union, intersections. Okay, fine. I'm still waiting for the axiomatic definition of probability. You have problems, you can solve them, should be simple. Okay, now here comes axiomatic definition of probability. Okay, let's look at some axioms. Uh, some sigma field, sigma algebra. I think camp students will know. I don't know. I think they are more accustomed to looking at words like fields, rings, and so on. But I don't know. I'll just go on groups for that matter. Okay, what are the axioms? Probably okay. Three axioms are there. Probability of any event A is non-negative in the sense greater than or equal to zero. Fine. Probability of the entire sample space is one. Nice. It means all possible events are there in the sample space. No, so if I take the probability of that, you'll get one. If you're getting less than one, it means something is missing in your sample space. If you're getting more than one, that means you're doing some sort of magic, I suppose, because probability can't be more than one. Uh, if A and B are mutually exclusive, what is mutually exclusive? It's like if A happens, then B can't happen. For example, if you get a tail, you can't get a head, and if you get a head, you can't get a tail. One more example is if it is day, it is not night, and if it is night, it is not day. And I'm not talking about sunrise, sunset, not that time. So yes, and any other example? If today is Monday, then it can't be Tuesday as well. So something like that, mutually exclusive. If one thing is happening, the other thing must not happen. So one question: if two events are mutually exclusive, does it mean they're independent? The answer is no. If two events are mutually exclusive, then they're dependent. Because see, if today is Monday, it can't be Sunday. So there is this sort of a dependence. So mutually exclusive events are dependent. And if two events are independent, then they can't be mutually exclusive. Like I just told the vice versa thing. Okay, anyways, what is the third axiom? If A and B are mutually exclusive events, then probability of A or B occurring is the sum of probabilities of A and B. So A union B is P. Okay, so interesting thing. So I'll just write this here. The third axiom. I'll just write two things. If A and B are independent, and if A and B are mutually exclusive. Mutually exclusive. So what is the property for independence? There the P of A and B will be a P of A into P of B. But the property for mutually exclusive events is probability of uh, A or B will be equal to P of A plus P of B. Why is this the story? Because if A and B are mutually exclusive, it means they have nothing in common. So the total probability will be nothing but the sum of their individual probabilities. That is mutually exclusive. If A and B are independent, can you give me two events that are independent? I mean, okay, fine. I'll not get into the theory much. So these are like two properties. One is for independent, the other is mutually exclusive. If A and B are independent, they can't be mutually exclusive. If A and B are mutually exclusive, they can't be independent. Because if they are mutually exclusive, it means they are indeed dependent in a way. Fine. So three axioms. Non axiom of non-negativity, axiom of I don't know unity. I don't know. Sum is one. I mean total probability is one. And then we have mutually exclusive thing. Fine. Oh okay, fine. Axiom of non-negativity, axiom of certainty, axiom of additivity. So that's just two events. You can have n events. So if all of them are mutually exclusive, or you can also call them disjoint, mutually disjoint, disjoint because they have nothing in common. Axiom of additivity. Nice. So axiomatic definition we understood. It's the same thing. So non-negative probability should be non-negative. Total probability is one, and if you have mutually exclusive events, the probability of their union is basically the sum of their individual probabilities. That is fine. Impossible event is zero. Okay, and we can write this. So probability of complement of A is nothing but 1 minus probability of A. That is also fine. So probability of complement of A and B. So it's like probability of complement of A and B. This is nothing but probability of 1 minus, not 1 minus, it's like the entire set. Let me say I have a universal set U minus A and B. What will this be? Will this be universal set intersection B? Minus means, okay, you write minus this way, right? I I'm just writing things. What is the intersection of universal set and B? It's essentially B. Am I even going somewhere? I have no idea. Is this taking me anywhere? B minus A. Okay, if I have A, if I have B, I just want to write A complement is this one. A complement is everything outside this. So this one as well. And intersection B, so only B. This is nothing but B minus A intersection B. B is this one, and I want to remove A intersection B. So that means it is only B. So I think I got the same answer. Only B, only B. It's the same answer. I'm just writing it in different ways. They have a better way, right? They wrote directly probability of B minus probability of A intersection B. Is that what they wrote? Okay, fine. There's nothing to memorize. Just you can draw the Venn diagram and then just keep finding things. Addition theorem of probability. So, in the axiom, we saw that if they're mutually exclusive, we can do some additions over there. What if they're not mutually exclusive? Then you're supposed to do this. Probability of A union B is probability of A plus probability of B minus probability of A intersection B. Now, if you look back, when you say two events are mutually exclusive, that would mean A intersection B will be a null set. So that is why the probability of union of two mutually exclusive events is nothing but probability of A plus probability of B. Uh, oh yes, so that is the next point. If A and B are mutually disjoint, then A intersection B will be a null set. Probability of a null set is 0. Done. You get your axiom. Uh, uh, Interesting. So if you have three non-mutually exclusive events, then you get probability of A plus probability of B plus probability of C minus. It goes on. It's like a pattern at this point. Is this in the syllabus? Sample space, conditional probability, independence of events, theorem of total probability. We'll have to go to the end. The end is these properties. It's simple. Just go through them. We saw something like this in TMS last time. Uh, we wanted to find the number of onto functions. So this looks very similar. This reminds me of that. Okay. Anyways, moving on. Uh, okay. Nice. Beautiful scenarios. Okay, this is there in the syllabus. Conditional probability. So P probability of A intersection B is nothing, or in other words, probability of A given B is nothing but probability of A and B divided by probability of A. That is conditional probability. But multiplication theorem is probability of A intersection B is nothing but probability of A into probability that B given A happened. Like, not happened, but probability of A into probability of B given A happened. Fine. Or the other way is also fine. Probability of B to probability of A given B happened. Mm, nice. Whichever one is easier to remember, you can remember the above one or the below one. The above one is basically multiplication theorem. The below one is basically the conditional theorem probability. but both of them are just the same formula. It's like they're just different representations. That's it. Uh, this is conditional probability. It's just a formula over here. And yes, if the events are independent, then probability if A and B are independent, then probability of A given B is nothing but probability of A. So that is what happens. So if you look at the multiplication theorem, if I say A and B are independent, then probability of B given A will be essentially probability of B, and probability of A given B will essentially be probability of A. So that is how this changes. That is how you get the probability of A intersection B is probability of A into probability of B. Uh, that was independent events. If you have exclusive, okay, let A and B be let A and B be mutually exclusive events with probability non-zero probabilities. Okay, fine. If they're mutually exclusive, it means A intersection B is a null set, so probability of A intersection B will be zero, and probability of A given B. Okay, so I will apply my multiplication theorem. Probability of A intersection B is nothing but probability of A, or I would say uh, probability of A into probability of B given A, right? Let me just write this. I can write that probability of A intersection B is probability of A into probability of B given A. But I just showed that this is 0 for A and B, which are mutually exclusive, right? Mutually exclusive. But I also told that the probability of A is not 0. I took that in the assumption that probability of A and B are non-zero probabilities. That would mean this has to be 0. So probability of B given A has to be 0, isn't it? Or A given B, whatever is the order. If probability of A given B has to be 0, I already know that probability of A is not 0. In other words, probability of A given B is not equal to probability of A. That would mean A and B are not independent. Because if A and B are independent, probability of A given B has to be probability of A. So this is how you can prove mathematically that two mutually disjoint events are not independent and hence dependent. This is one way of proving it. And therefore, if two events are mutually exclusive, it means they are always dependent. And the other way is also true. If you start with independent events, you will be able to show that it's the properties of mutually exclusive events are not being satisfied. Like, for example, probability of A intersection B. If they're mutually exclusive, it has to be zero. But here it's never zero. It's always non-zero. So independent events are never mutually exclusive. Mutually exclusive. Yes, fine. Independent events are never mutually exclusive. It means if two events are independent, it means their intersection will always be non-zero. So it's an interesting observation. Okay, more results. Probability of A union B given C happened is nothing but see, probability of A union B is what? It's just probability of A plus probability of B minus probability of A intersection B. Now, since given C is there for everything, you just add given C. However, you want to remember, you can remember. I will just keep going. Okay, if the events are pairwise independent, if they're independent, I can just split the probability into their product. So probability of A and B will be probability of A into probability of B. Uh, okay, there is some proof here. What proof in the sense there is some relation. Probability of A intersection B will always be less than or equal to probability of A plus probability of B. The proof is in between. It's just that it's just there. So this is some relation. That's it. Right? Nice, nice relation. Okay, more problems. Problem. What's in the syllabus though? Where is theorem of total probability? And where is Bayes theorem? Bayes theorem, Bayes theorem. Okay, total probability. So this is the second last topic of unit 1. So it's 117. It's just two more topics. Then okay, I think this will be the first subject where I covered all the topics. Covered in the sense at least most of the topics. I just skipped the basic topics, right? I didn't get into the details of all examples or whatever. Okay, fine. Total probability. What is total probability? Okay, we're like partitioning something. Okay, fine. Where is so probability of A is nothing. Okay, there's law of total probability. Probability of A is nothing but probability of A given B into probability of B plus probability of A given B complement to probability of B complement. Uh, okay, nice. What do we mean by this? So we'll just look at the definition. Maybe it will make sense. If B1, B2, B3 are partitions, okay, if this entire thing is a partition of the sample space S, then for any event A, we have probability of A is equal to, okay, fine. So, oh, the picture is here only. It's like there is some event A. Within event A, you have different partitions. Let's say B1, B2, B3, or let's say you have until Bn. So you have many, many, many partitions. Finally, you reach Bn. And we know that if you take the union of all Bi's, you will get your event A. So you want to find the probability of A. But A is nothing but, oh, I can write this as a probability of A intersection Bi summation I is going from 1 to n. What does it mean? It's like A intersection B1 is this one, A intersection B2 is this one, A intersection B3 is this one. So on, I will keep adding until A intersection Bn. So finally, I'll get my A only. So I can write it this way. There's no problem. This is fine. Now I think we are applying some properties. What is A intersection Bi? Probability of A intersection Bi. What will that give us? Uh, and okay, is there any properties of B of these events? All of them are mutually exclusive. If you see, there is no element that is common to two different BIs. So they're all mutually exclusive. And do we have any property for mutually exclusive? We do, but that is for A union B. This is A intersection B. Let me just go back and see what did they do with this now. Okay, they're using fine. They're simply using the multiplicative multiplication theorem. What does the multiplication theorem say? This is nothing but probability of uh, you have two different ways of writing this. So I will write one way. Uh, it's either this and given this happened, or you can choose to write probability of A, but probability of Bi given A happened. So it's either this or this. I think we will be going with the first one. I think. Let me just verify that. We just used multiplication theorem. It says that if you have probability of A intersection B, it is equal to probability of A into probability of B given A happened, or it is equal to probability of B into probability of A given B happened. It's any of this. This is the multiplication theorem. In case A and B are independent, you can just remove the given part. That is fine. But we know here, what do we know? Oh, we know nothing. A and B are not mutually. Each of them are mutually disjoint, but A and B are not mutually disjoint. Uh, what did they choose? Did they choose? Okay, they chose this, the first form. They chose the first form. Fine, fine. So total probability. It's like I made n different cases. So B1, B2, B3, B4. I made I have now n events. I split my main event into seven, not seven. I split my main event into n different events. I mean, this is the mathematic. This is one way of showing how did we another way. So P of A is nothing but P of A is nothing but okay. Here they used A1 A2. I could use B1. I mean, whatever you do, you'll just land up at the same formula. So I don't think we have to break our heads or anything. They're just finding different ways of writing the same thing. Here A1, A2, A3 are okay. Here, okay, it's up here. A1 is A intersection B1, A2 is A intersection B2, A3 is A intersection B3. Fine. So A1, A2, A3 are mutually exclusive, right? And if they're mutually exclusive, A1 union A2 union A3, I can split them. I can. This is from the third axiom. If you have mutually exclusive events, I can just split them up and write them as a sum of their individual probabilities. This is what they wrote there. And I know A1 is nothing but A intersection B1. A2 is nothing but A intersection B2. A3 is nothing but A intersection B3. So summation of all of this, and I know that by multiplication theorem, probability of A intersection Bi is nothing but probability of Bi into probability of A given Bi. Nice. You can look at examples. So in order to make this picture accurate, I will. So you have something like this. This is B1. This is Bn, and then you have something like this. This is A. So you have A1, A2, and so on. This is An. Nice. So summation of A intersection Bi will give me my A back. Nice. Total probability. There is one formula. You can use it in different places. You can just look at the examples. Last topic. Last topic. Bayes theorem. So you want to find posterior probabilities. Mm, it's like I think Sir gave some example. It was about some party where it's like some n number of people wore red shirts to the party, and they told like let's say 100 people came wearing red. Okay, 100 is too much. Let's say 5 people came to the party wearing red shirts, and some other people wore other shirts, some number. And when okay, we'll just look at the examples that they give. Maybe I can't frame one right off the bat. Okay, let's read the theorem. If A1, A2, and so on until AN are mutually disjoint events with non-zero probabilities, then for any arbitrary event E, which is a subset of the union set of AI, such that probability of E is also non-zero, then we have something. Okay, I think this diagram should help us. It's very similar to the total probability thing, right? We have some box, we drew some event around that. Okay, let's see. 1 minute. We'll just read a question, then we'll come back. In 2022, there were three candidates for the position of principal: Mr. Chatterjee, Mr. Iyengar, and Dr. Singh, whose chances of getting the appointment are in the proportion of 4 is to 2 is to 3, respectively. We have some information now. The probability that Mr. Chatterjee, if selected, would introduce co education in the college, okay, is zero point 0.3. The probability that he will do that is 0.3. Whereas the probabilities for Mr. Iyengar and Dr. Singh doing the same are zero point 0.5 and 0.8, respectively. What is the probability that there was co education in the college? Hmm. So they didn't get selected yet. So it's like if if any of them gets selected, then there is some probability that they would introduce co-education, and they're asking what is the probability that there was co-education. So co-education could have been introduced by either Mr. Chatterjee, Mr. Iyengar, or Dr. Singh. We wouldn't know. So we'll have to sum the probabilities. I think that is where the summation in Bayes' theorem comes from. So okay, so in the question, what will A1, A2, A3, and so on? Okay, there are only three events: A1, A2, A3, and capital E is the event of introducing co-education. So A1 will be Mr. Chatterjee being selected. A2 will be the event where Mr. Iyengar is selected, and A3 will be the event in which Dr. Singh is selected. So we have four events: A1, A2, A3, and capital E. So what is probability of A1 given E? Am I even choosing this right? Should it be this one? Or because probability of A1 given E makes no sense. Probability of A1 given E would be probability that Chatterjee will be selected given co-education is introduced. Uh, okay, maybe that's why it says posterior probabilities. Fine, fine. Is that how it is? No answers here. Fine. Let me just okay. We'll solve this then. We'll solve one problem. We'll solve this problem using Bayes theorem. So what was the probability of proportion again? 4 is to 2 is to 3, right? So we'll write A1, A2, A3. So this was like 4 is to 2 is to 3. This was Chatterjee. This was Iyengar. This was Singh. And what is the probability that co-education is going to get introduced? Point 0.3, point 0.5, point 0.8, 358. So, okay, so what is, I told you, right? A1 is the probability that Chatterjee is going to get selected. A2 is not probability, event. A2 is the event in which Mr. Iyengar is selected. A3 is the event in which Dr. Singh is selected. Uh, E is the event in which co education is introduced. Okay, let me write it neatly. So, A1 means C is selected, so Chatterjee is selected. A2 means Iyengar is selected. A3 means sing is selected, and E means co-education is introduced. So I have four events. That is fine. Four events I have, and 4:2:3 means 4, 5, 6, 7, 8, 9. So probability of A1 is 4 by 9. Probability of A2. How did I get 9? 4 plus 2 plus 3 is 9. Probability of A2 is 2 by 9. Probability of A3 is 3 by 9, or you can write 1 by 3. That is also fine. Now, what are these values? 0.3 is the probability that Mr. Chatterjee will introduce co-education if he is selected. So that would mean probability of uh, E happening if only if A1 happens. Like probability of co-education being introduced given that A1 is selected, given that Chatterjee is selected. This is 0.3. So I'm just writing the question in terms of probabilities. Then we will look into Bayes theorem later. Probability of E. Let me write it here. So probability of co-education being introduced given Chatterjee is selected, it is given to be 0.3. Probability of co-education being introduced given Mr. Iyengar is selected. This is there. Probability of Dr. Singh being select. Probability of co-education being introduced given who is this person? Dr. Singh is selected. That is how much? Oh, sorry, this is not 2 by 9. This is 0.5, and this is 0.8. Now the question is, what is the question? The question is asking, what is the probability that co-education is going to be introduced in this? Which is a college. Uh, yes. So what is the probability that there was co-education in the college in 2023? Essentially, they're being selected, right? So fine. So we have to find this using Bayes theorem. So we don't know who's getting selected. It's either Chatterjee, Iyengar, or Dr. Singh. We don't know. But what our interest is? What is our interest? We want to find what is the probability of E. We have everything required for that. We just have to know what is Bayes theorem. What is Bayes theorem? So Bayes theorem is this. Uh, where is Bayes theorem? I mean, I can just send P of E to the left hand side and send this to the bottom, right? Yes. If you notice here, uh, using total probability, I can write P of E as summation of PAI into P of E given AI, right? This is the we're using total probability in the denominator. Nice. So I just have to write P of E. So P of E is nothing but let me just do some maths now. P of E. Wait, did I read the question right? Okay, yes, I read the question right. Fine. So P of E, P of AI given E. This is nothing but P of AI. Or let me write this at the P of E into P of AI given E is nothing but P of AI into P of E given AI. This is using the multiplication theorem. I'm just writing how because this is nothing but P of A intersection EI, E intersection AI. I'm just writing this for some reason. I think Bayes theorem came from here somewhere. What do I need? I need P of I, P of E, right? I need P of E. So that would mean I have to do this. Uh, but do I have this piece of information? I don't. I have this information. I have this information. Okay, so I have to take the sum then. Right. So if I take the sum across all i's, what will happen? Will this relation be valid? It's like I'm deriving Bayes' theorem at this point. I mean, can I rewrite the denominator? My goodness. Okay, let me just read the theorem. If A1, A2, and so on until AN are mutually disjoint events, mutually disjoint. Yes, Chatterjee, Dr. Singh, Iyengar, only one will be selected. For any arbitrary event E, which is introduction of the coeducation, uh, eh, this is not a subset of, okay, fine. So E is not coeducation, fine. In this case, fine. Shouldn't it? Uh, uh, Fine, let me just see. Okay, okay. So probability of AI given E is nothing but probability of AI intersection E by probability of E. And probability of E is nothing but using the total theorem, I can write it as a summation probability of AI into probability of E given AI. So I will get the denominator using, so I have to use Bayes theorem here. Okay, nice. So I have to use the Bayes theorem to find these values, probability of A1 given E. Now I should use Bayes theorem. What is the Bayes theorem? See, Bayes theorem, it came from here. So probability of A1 is, or let me say generally AI. What is probability of AI given E? Probability of AI given E is probability of AI intersection E divided by probability of E. But what is probability of E? Uh, I using total probability, I can write that probability of E is nothing but summation probability of AI into probability of E given AI. This is using total probability. I can write this. What is my numerator going to be? AI and E. Here AI is the Chatterjee and all those people getting selected. And I mean here also you can use my okay, here I'll use my multiplication theorem. So here what will happen? Here I'll get probability of AI into probability of E given AI. Fine. So probability of E is going to be summation of probability of AI given E. So okay, fine. So this is Bayes theorem. There's nothing to memorize though, but this is Bayes theorem. This part is Bayes theorem. It came from total probability. I used total probability here. Nice. It's like every now and then I look at Bayes theorem. Like after a few weeks or something, or few months, I'll have to go through this process again because I wouldn't remember what is Bayes theorem. Now it is clear, but after a few weeks, maybe I'll forget what's Bayes theorem. I'll have to go through this process once again. Okay, so probability of E is summation of all of this. Why? Because they're all mutually disjoint, right? Chatterjee coming in, introducing co-education. Iyengar coming in, introducing co-education. No, that is not what this means. But anyways, what is the meaning of this? The meaning of this is uh, probability that Chatterjee was selected given co-education is introduced. That is the meaning. So in order to find such kinds of probabilities, you have to use Bayes theorem because we only have information about probability of co-education being introduced given a certain person was selected. Bayes theorem is like the opposite. Probability of someone being selected given that co-education is introduced. So it's like the opposite. So in those cases, Bayes theorem will help us. So this is Bayes theorem. Bayes theorem. So I want to find what is the probability that co-education has been introduced. It could have been introduced by either uh, any of those three persons. So I can either do this or I can either do this one. Probability of uh, no, I mean you can't. This is the only thing. So using Bayes theorem. So what will I get? Summation. I mean just find the individual probabilities and add them. You'll get them. So it's like P of A1 given E plus P of A2 given E plus P of A3 given E. So we'll first find these things. What is probability of A1 given E? So probability of A1 is 4 by 9. 4 by 9. I'm just applying Bayes theorem into probability of E given A1. This is 0.3. Denominator I will look into it later. 2 by 9 into 0.5. 2 by 9 into 0.5. Here it is 1 by 3 into 0.8. 1 by 3 into 0.8. What is denominator? Denominator is the same for everything, uh, which is uh, which is probability of E. So denominator is probability of E, and probability of E is not given. So fine, just find probability of E then. Aren't we going in circles though now? Oh, fine. So uh, I just have to find probability of E, right? So I don't have to even use Bayes theorem. I can directly find it out because, right? I can directly find it out. I know probability, total probability I'm using. Probability of E is nothing but I'm using total probability. I don't need Bayes theorem. I'm going in circles. But anyways, Bayes theorem is here, total probability is here. So what will this be? This will be 4 by 9 into 0.4 by 9 into 0.3 plus 2 by 9 into 0.5 plus 3 by 9 into 0.8. Fine. That is total probability. That was not Bayes theorem. I think now that we also saw what was Bayes theorem, you can just use it. The opposite. I've given you an example, the opposite. Fine, interesting. You can try solving the problems, or you could go through the tutorial solutions. Uh, nice. So it's too late now, 1:47. So I will end this stream now. End stream.